Imagine holding something in your hand that weighs almost nothing. Something so light, so impossibly delicate, that it seems to defy the very laws of physics we've come to understand about the material world. Now imagine that this same ethereal substance, this wisp of matter, can support the weight of a brick without collapsing. This is aerogel, and it represents one of the most extraordinary materials ever created by human hands. Let's begin with something tangible, something you can visualize. Picture a cube of aerogel, roughly the size of a basketball. You hold it in your hands, and it weighs less than a single AA battery. That's right, this basketball-sized object weighs less than the small battery you might pop into a television remote or a child's toy. And yet, despite this almost absurd lightness, you could place a brick on top of it, and it would hold. The brick wouldn't fall through. The aerogel wouldn't crumble. It would simply support it. This paradox, this seemingly impossible combination of lightness and strength, is what makes aerogel so fascinating to scientists and engineers alike. The relationship between weight and strength in aerogel challenges our intuitive understanding of materials. We're accustomed to a world where heavy means strong, where substance equals durability. A steel beam is strong because it's dense, solid, heavy. But aerogel operates on entirely different principles. Its strength comes not from density, but from structure, from the intricate lattice of molecules that form its skeleton, creating a three-dimensional network that distributes force in remarkable ways. People have given aerogel many names over the decades since its discovery, but perhaps the most poetic, the most evocative, is frozen smoke. When you look at aerogel, this description makes perfect sense. It appears as solid mist, as if someone had taken a cloud, a wisp of fog from a morning meadow, and somehow convinced it to hold still, to maintain its form without dispersing into the air. The material has an otherworldly quality, something that doesn't quite look real, as if it belongs more to a dream than to the physical world we inhabit. This appearance isn't merely aesthetic. It tells us something fundamental about what aerogel actually is. The frozen smoke appearance emerges from the material's structure at the nanoscale, where tiny particles of silica form chains and clusters suspended in space. Light interacts with these structures in unusual ways, creating that characteristic misty, ephemeral look that has captivated observers since aerogel was first synthesized in the early 1930s by Samuel Kistler, a scientist who was simply trying to answer the question: what would happen if you could remove all the liquid from a gel without allowing it to collapse? Speaking of light, there's something particularly beautiful about how silica aerogel interacts with illumination. When light passes through certain types of aerogel, the material glows with a smoky blue haze. This isn't just a curious visual effect. It's the same phenomenon that colors our sky. The blue glow comes from Rayleigh scattering, the process by which small particles scatter shorter wavelengths of light more effectively than longer wavelengths. In Earth's atmosphere, nitrogen and oxygen molecules scatter blue light from the sun, painting our daytime sky in shades of azure. In aerogel, the nanoscale structure of the material scatters light in exactly the same way. This connection between aerogel and the sky is more than just coincidental. It reveals something profound about scale and structure. The particles in aerogel that cause this scattering are comparable in size to the wavelengths of visible light, just as the molecules in our atmosphere are the right scale to scatter sunlight. When we look at aerogel glowing blue, we're seeing the same physics that makes a clear day beautiful, the same principles operating at a completely different scale. It's a reminder that the universe often repeats itself, that the same rules apply whether we're looking at molecules or at the vast expanse of atmosphere above us. But perhaps even more striking than aerogel's blue glow is how sometimes it almost isn't there at all. Many aerogels appear almost invisible, and this near invisibility stems from a specific optical property. Their refractive index is remarkably close to that of air. The refractive index measures how much light bends when it passes from one material to another. When you put a straw in a glass of water, the straw appears to bend at the water's surface because water and air have different refractive indices. But when two materials have nearly the same refractive index, Light passes between them without bending significantly. The boundary between them becomes difficult to see. This is what happens with aerogel. Because its refractive index is so similar to air's, light passes through with minimal distortion. The result is a material that can be almost impossible to detect visually except for that faint blue haze we mentioned, or perhaps a slight shimmer at its edges. You could hold a piece of aerogel in your hand and find yourself momentarily confused, your eyes insisting there's nothing there, while your sense of touch confirms something solid rests against your palm. This near invisibility has practical applications. Aerogel can be used in windows that insulate without blocking light. But it's also simply marvelous, a material that seems to exist at the very edge of visibility. The reason for all these unusual properties becomes clearer when we consider what aerogel actually is in terms of composition. Aerogels are typically 90 to 99.8% air by volume. Let that sink in for a moment. These are solids that are, in some cases, more than 99% air. They contain so little actual matter that calling them solids almost seems like a category error. And yet they are solid. They maintain their shape. They have structure and form. They are, in essence, carefully organized emptiness, scaffolding made from the bare minimum of material necessary to define a three-dimensional space. This extreme porosity is achieved through a special manufacturing process. Traditional gels, like the gelatin desserts you might have eaten, or the gel in a silica packet, contain a solid network suspended in a liquid. If you simply let that liquid evaporate, the surface tension of the liquid pulls the solid structure inward, causing it to collapse. The gel shrinks dramatically, losing its form. But in the production of aerogel, the liquid is removed through a process called supercritical drying, which avoids this collapse. The liquid is converted to a supercritical fluid, a state where the distinction between liquid and gas disappears, and then this fluid is vented away without ever forming a liquid-gas interface that would create destructive surface tension. What remains is the solid network, mostly unchanged, suspended in air. The result of this process is a material with astonishingly low density. Aerogel densities can be as low as 0.001 to 0.02 grams per cubic centimeter, making them the lightest solids ever created. To put this in perspective, water has a density of 1 gram per cubic centimeter. Air itself has a density of about 0.0012 grams per cubic centimeter at sea level. Some aerogels are only slightly denser than the air around them. They are, in a very real sense, barely there at all. They occupy space, but they contain almost nothing. They are the ultimate minimalist material, achieving solidity with the smallest possible commitment to actual matter. This extreme lightness comes with an unexpected benefit: an enormous surface area. A single gram of aerogel can have the surface area of a basketball court. This seems impossible at first. How can something that weighs as much as a single paperclip have the surface area of a space large enough to play basketball? The answer lies in the material's porous structure. Aerogel is filled with countless tiny pores, channels, and cavities. If you could somehow unfold all those internal surfaces, spread them out flat, you'd discover that this gram of material has an enormous total surface area, most of it hidden within the structure itself. This property makes aerogel incredibly useful for applications that depend on surface area. Chemical reactions often occur at surfaces, so a material with vast surface area can act as an exceptional catalyst or catalyst support. Aerogels can absorb substances, oils, toxins, contaminants, because there's so much surface area for those substances to adhere to. In a sense, aerogel structure is like a microscopic labyrinth, a three-dimensional maze with walls everywhere, and every surface is an opportunity for interaction with the surrounding environment. Despite being mostly air, despite weighing almost nothing, some aerogels can support thousands of times their own weight. This is perhaps the most counterintuitive property of all. We expect fragile things to be weak. We expect materials that are 99% air to collapse at the slightest touch. But aerogel can be surprisingly strong in compression. That brick sitting on a basketball-sized cube? It represents a load thousands of times the weight of the aerogel itself, and yet the material holds. The strength comes from the distribution of forces through the interconnected solid network. When you press down on aerogel, the force spreads through countless microscopic struts and connections, each one bearing a tiny fraction of the total load. Together, they can support remarkable weight. Of course, this strength has its limits and its quirks. Aerogel feels like a fragile styrofoam cracker, brittle yet oddly elastic. If you've ever held aerogel, you know this sensation. It's delicate, certainly. Apply force in the wrong way, and it can crack or crumble. But it also has a springiness to it, a slight give. Press gently on it, and it compresses slightly before resisting. It's neither quite as fragile as glass, nor quite as robust as plastic. It occupies its own category of tactile experience, something between a wafer cookie and packing foam, but not quite like either. This unusual texture is another consequence of its structure. Those microscopic struts can bend slightly under force, giving the material some elasticity, even as the overall structure remains brittle. And then there's one more unexpected property. Some aerogels transmit sound slower than almost any other solid. Sound travels through materials as a wave of compression, passing from molecule to molecule. In dense materials like steel, sound travels very quickly, around 5,000 meters per second, because the molecules are packed closely together, allowing vibrations to transfer efficiently. But in aerogel, there's so little actual material that sound must travel along a tortuous path through the sparse solid network. The result is that sound moves slowly, sometimes at speeds approaching the speed of sound in air rather than in solids. This makes aerogel useful for acoustic insulation and dampening, but it's also just another example of how this material defies our expectations at every turn. Aerogel challenges us to reconsider what it means for something to be solid, to be strong, to be substantial. It exists at the boundary between matter and space, between presence and absence. It is almost nothing, yet it is demonstrably something. In our everyday lives, we rarely encounter materials that force us to think about these fundamental categories. But aerogel does exactly that. It is frozen smoke and solid air, weightless strength and visible emptiness. And as we continue to explore its properties and discover new applications for it, aerogel reminds us that the material world still holds surprises, that there are still substances waiting to be discovered or created that will make us pause and wonder at the possibilities of matter itself. To truly understand aerogel, to grasp why it behaves in such extraordinary ways, we need to journey into a realm invisible to the naked eye. We need to shrink ourselves down, in our imagination, to a scale where the width of a human hair seems vast, where bacteria would tower like buildings. We need to enter the world of the nanometer, where 1/1000th of a meter becomes our unit of measurement, and where the structure of aerogel reveals itself in all its intricate complexity. Aerogels are made from a nanoscale network of solid struts and pores. Picture, if you will, a vast three-dimensional scaffold, like the framework of countless buildings interconnected in every direction. But instead of steel beams meters thick, imagine struts so thin that thousands could fit across the width of a single human hair. These struts connect at nodes, forming chains and clusters, creating a continuous solid pathway that winds through space. And between these struts, everywhere, there is emptiness, pores filled with air, creating that remarkable porosity we discussed earlier. This isn't a regular, orderly structure like a crystal lattice. There's no perfect symmetry here, no repeating pattern. Instead, the network is random, chaotic in its organization, yet continuous throughout. It's more like a tangled web than a carefully designed architecture, the result of chemical processes that create connections wherever molecules happen to meet during the gel formation process. Every piece of aerogel has a unique internal structure, a one-of-a-kind maze of matter and void, frozen in place by the manufacturing process that removed the liquid without allowing collapse. The pores themselves, those empty spaces between the solid struts, have typical sizes measured in tens of nanometers across. To give this some context, a nanometer is 1/1000th of a meter, The pores in aerogel might be 20, 30, 50 nanometers wide. A virus particle might just barely fit inside one of these pores. A typical protein molecule would have room to move around. These are spaces at the very edge of what we might call structure, dimensions where the quantum nature of matter starts to become relevant, where individual atoms matter in determining behavior. The size of these pores isn't arbitrary. It's crucial to aerogel's properties. If the pores were much larger, the material would simply be a foam, and it would lose many of its special characteristics. If they were much smaller, the solid network would occupy more volume, making the material denser and less remarkable. But at tens of nanometers, something special happens. The pores are large enough that the material remains mostly air, yet small enough that they create extraordinary surface area and begin to interfere with the fundamental processes of heat transfer. And what surface area it is? This nanoscale structure creates enormous internal surface area, up to about 1,000 square meters per gram. We mentioned earlier that a gram of aerogel could have the surface area of a basketball court, and now we can be more specific. 1,000 square meters is indeed roughly the size of a basketball court, actually somewhat larger, about half the size of 2 basketball courts placed side by side. All of that surface area, crumpled and folded and packed into something that weighs as much as a single raisin. This vast internal surface emerges from geometry. Each strut in the network has a surface. Each pore has walls. When you have billions upon billions of pores, each one tiny, each one adding its walls to the total, the surface area accumulates at an astonishing rate. It's similar to how crumpling a piece of paper doesn't change its surface area if you could smooth it back out perfectly. But aerogel takes this principle to an extreme. It's like taking that paper and folding it into ever smaller creases, creating new surfaces at every fold, until you've transformed a simple sheet into an impossibly intricate origami sculpture of nearly infinite complexity. This enormous surface area makes aerogel valuable in chemistry and industry, but it's also connected to another of aerogel's most celebrated properties: its exceptional ability to prevent heat transfer. To understand this, we need to think about how heat actually moves from one place to another. Heat, fundamentally, is the motion of molecules. In a hot object, molecules vibrate rapidly. In a cold object, they move more slowly. When a hot object touches a cold one, the rapid vibrations of the hot object's molecules gradually transfer energy to the slower-moving molecules of the cold object, eventually bringing both to the same temperature. This transfer can happen in 3 main ways: through solid materials, through gases, and through the bulk motion of fluids called convection. Aerogel, remarkably, suppresses all 3 of these heat transfer mechanisms simultaneously. Let's begin with heat conduction through solids. In a typical solid material, say a metal rod, heat travels quite efficiently. Molecules in the hot end vibrate intensely, bumping into their neighbors, causing them to vibrate more intensely as well. This energy cascades through the material, sometimes assisted by the movement of electrons in conductors like metals. The denser and more continuous the material, the more efficiently this transfer occurs. But in aerogel, the solid pathways are extremely thin, minimizing heat conduction. Remember those nanoscale struts we discussed? They're so thin, and they constitute such a small fraction of the material's volume, that there's simply not much solid material for heat to travel through. The heat that does conduct through these struts must take a tortuous, winding path through the network, slowing the transfer significantly. Imagine you wanted to cross a room, but instead of walking directly across an open floor, you had to navigate a maze of narrow bridges suspended in space, with most of the room being empty air. You'd reach the other side eventually, but it would take much longer than a direct path. This is essentially what happens to heat trying to conduct through aerogel's solid network. But what about the air itself? After all, aerogel is up to 99% air by volume. Surely heat could simply conduct through all that air? Under normal circumstances, it could. Air isn't a great conductor of heat, but it does conduct some. However, in aerogel, something interesting happens. Gas molecules collide with pore walls before transporting much heat. In open air, a molecule can travel some distance, called the mean free path, before colliding with another molecule. At room temperature and atmospheric pressure, this mean free path is about 60 to 70 nanometers. A molecule bouncing around at random will, on average, travel this distance before hitting another molecule and exchanging energy. But remember how large the pores in aerogel are? They're tens of nanometers across. This means that many of the air molecules inside aerogel's pores don't travel far enough to collide with other air molecules. Instead, they collide with the pore walls first. When a molecule hits a solid wall, it bounces off, often losing some energy to the wall or gaining energy from it. This interrupts the normal process of heat conduction through the gas. Instead of energy flowing smoothly from molecule to molecule through the gas, each molecule is constantly interacting with the solid structure, disrupting the transfer. The gas trapped in these tiny pores can't efficiently transport heat because the molecules keep running into walls before they can establish a smooth flow of energy. And there's another mode of heat transfer we haven't addressed yet: convection. When you heat air, it expands and becomes less dense, causing it to rise. Cooler, denser air sinks to replace it. This circulation, convection, can transport a lot of heat. It's how a pot of water boils, how weather systems develop, how a radiator warms a room. But in aerogel, pores are too small for convection to occur. You need a certain amount of space for the bulk motion of fluid to develop. In tiny pores measured in nanometers, there simply isn't room for convection currents to form. The air molecules are trapped in spaces so small that they can't organize into the flowing patterns that would transport heat efficiently. So we have a material where solid conduction is minimized by thin, sparse struts, where gas conduction is disrupted by constant collisions with pore walls, and where convection is impossible due to tiny pore sizes. All three heat transfer modes, solid, gas, and convection, are suppressed simultaneously. This is extraordinarily rare. Most insulating materials block one or two of these mechanisms well, but struggle with the third. Aerogel manages to suppress all three at once. The key to this remarkable performance lies in a specific relationship between pore size and molecular motion. Pore sizes approach or fall below the mean free path of gas molecules. We mentioned that the mean free path, the average distance a molecule travels between collisions, is about 60 to 70 nanometers for air at normal conditions. The pores in aerogel are often comparable to this size or smaller. This is the sweet spot for insulation. When pores are much larger than the mean free path, gas molecules can move freely, conducting heat efficiently. When pores are much smaller than the mean free path, you don't have much room for insulating gas at all. But when pores are roughly the same size as the mean free path, or slightly smaller, you've trapped gas in spaces too small for it to conduct heat well, while still maintaining enough open volume to keep the material's density extremely low. It's a delicate balance, achieved through careful control of the aerogel's synthesis. This precise engineering of structure at the nanoscale allows aerogels to outperform still air as insulation. Think about that for a moment. Still air, the absence of wind, just calm atmosphere, is already quite a good insulator. It's why double-paned windows trap air between the panes, why down jackets trap air between feathers, why foam insulation is full of tiny air bubbles. Air itself is hard to beat as an insulator, but aerogel beats it. How can a material that's mostly air insulate better than pure air? Because pure air, even still air, can still conduct heat through molecular collisions and, in any real situation, can develop convection currents. But the air trapped in aerogel's nanoscale pores can do neither effectively. The aerogel's structure immobilizes the air, preventing convection entirely and disrupting conduction. Meanwhile, the tiny amount of solid material present contributes so little to heat transfer that the overall performance surpasses what air alone could achieve. The result of all this, of the precise pore sizes, the minimal solid content, the suppression of all three heat transfer mechanisms, is some of the lowest thermal conductivity ever measured in a solid. Thermal conductivity is the measure of how well a material conducts heat. High thermal conductivity means heat flows easily through the material. This is desirable in cooking pots, but undesirable in insulation. Low thermal conductivity means heat flows very slowly, exactly what you want in insulation. Aerogels can achieve thermal conductivities as low as about 0.013 watts per meter Kelvin, and some specialized aerogels go even lower. To put this in context, air itself has a thermal conductivity of about 0.025 watts per meter Kelvin. Fiberglass insulation, commonly used in buildings, has a thermal conductivity of about 0.04 watts per meter Kelvin. So aerogel can insulate roughly twice as well as fiberglass per unit of thickness, and better than air itself. This exceptional insulating ability has led to aerogel being used in remarkable applications. NASA has used aerogel in spacecraft, where minimizing weight while maximizing insulation is crucial. The Mars rovers have used aerogel in their instruments to protect sensitive equipment from the extreme temperature swings on the Martian surface. Some high-performance outdoor clothing incorporates aerogel to provide warmth without bulk. There are even aerogel blankets, thin sheets of aerogel that can protect your hand from a blowtorch flame held just inches away, conducting so little heat that you feel almost nothing. Imagine holding such a material in your hand. On one side, a flame hot enough to melt metal. On the other side, your skin, completely comfortable, feeling barely any warmth. The heat is trying to flow through the aerogel, but the journey through those nanoscale pores, interrupted by countless collisions with strut walls, slowed by the tortuous path through the sparse solid network, becomes so difficult that almost no heat completes the crossing. The flame continues to burn, the energy continues to radiate, but the aerogel stands between, a barrier made of almost nothing, holding back the flow of heat through its clever architecture of emptiness. This is the hidden power of structure at the nanoscale. We often think of materials science as being about chemistry, about what elements and molecules make up a substance. And chemistry matters tremendously. But aerogel reminds us that how those molecules are arranged in space can be just as important as what those molecules are. The same silica that forms dense glass or loose sand can, when organized into this specific network of nanoscale struts and pores, become one of the most effective insulators humanity has ever created. As we consider aerogel's thermal properties, we're really contemplating a deeper principle. That at the smallest scales, the details of structure begin to control behavior in profound ways. The nanoscale isn't just a miniaturized version of the world we see around us. At these dimensions, different rules start to dominate. The mean free path of molecules becomes relevant. Surface area becomes more important than volume. And materials that seem paradoxical at human scales, solids made almost entirely of air, become not just possible, but extraordinarily useful. In our next segment, we'll explore how aerogel came to be, the history of its discovery and development, and the various forms this remarkable material can take. But for now, rest with this image. A network of gossamer struts, tens of nanometers thick, stretching through space, creating a labyrinth of pores that trap air, suppress heat, and achieve through structure what dense materials cannot achieve through mass. This is aerogel at its most fundamental level, a testament to what becomes possible when we learn to build at the scale of viruses and molecules, when we architect emptiness itself into something useful and profound. We've established that aerogel is an exceptional insulator, suppressing heat transfer through its ingenious nanoscale architecture. But to truly appreciate the extremes of its insulating capability, we need to venture into the realms of temperature that exist far beyond our everyday experience, into the bitter cold of cryogenic systems and the searing heat of aerospace applications. This is where aerogel's properties become not just impressive, but genuinely extraordinary. Some silica aerogels reach thermal conductivities as low as about 0.003 watts per meter Kelvin. Let's pause on this number for a moment, because it represents something quite remarkable. Earlier, We mentioned that typical aerogels might achieve thermal conductivities around 0.013 watts per meter Kelvin, already better than nearly any conventional insulating material. But through careful optimization, controlling the pore size distribution, minimizing the thickness of solid struts, sometimes evacuating some of the air from the pores, researchers have pushed this value even lower, down to 0.003. This is nearly an order of magnitude lower than air itself, and several times better than the best fiberglass insulation. To put it in practical terms, a panel of this optimized aerogel, just a few centimeters thick, could insulate, as well as a much thicker layer of conventional insulation. In applications where space is limited, in spacecraft, in specialized equipment, in portable containers, this difference between acceptable performance and exceptional performance can determine whether something is possible at all. But numbers on a page, specifications in a technical manual, these don't always capture the reality of what a material can do. So let's talk about what aerogel can actually protect you from, starting with the extreme cold. Aerogels can insulate against liquid nitrogen at -196 degrees Celsius. Liquid nitrogen is cold in a way that's difficult to comprehend if you've never encountered it. At -196 degrees Celsius, it exists as a boiling liquid at atmospheric pressure. This is cold enough to freeze almost anything instantly. Dip a flour in liquid nitrogen, and it becomes so brittle it shatters like glass. Pour it on the ground, and it forms a pool that boils violently, evaporating in seconds while creating clouds of condensed water vapor. Expose unprotected skin to liquid nitrogen, and you'll suffer frostbite in moments, as the tissue literally freezes solid. Yet aerogel can stand between you and this extreme cold, maintaining a temperature gradient so steep that one side touches liquid nitrogen, while the other remains near room temperature. The heat from the warmer side tries to flow toward the extreme cold, as heat always does, seeking equilibrium. But the journey through aerogel's nanoscale maze is so difficult, so impeded by the structure we've discussed, that the heat flow slows to a trickle. The liquid nitrogen continues to boil, yes, but the rate at which it steals heat from the other side of the aerogel is remarkably slow. This capability has practical implications that go beyond laboratory curiosities. Aerogel-insulated clothing can remain wearable at cryogenic temperatures. Imagine working in an environment where you're constantly exposed to materials at -196 degrees Celsius or colder, perhaps in a facility that handles liquid nitrogen, liquid hydrogen, or other cryogenic fluids used in industrial processes, medical applications, or rocket fuel systems. Ordinary clothing would be useless. Even specialized cold weather gear, designed for Arctic expeditions, wouldn't come close to protecting you. The cold would penetrate through conventional materials far too quickly. But clothing incorporating aerogel can maintain a protective barrier, keeping your body heat from escaping while preventing the extreme cold from reaching your skin. The aerogel layer doesn't need to be thick. Just a thin panel or lining can provide extraordinary protection. And because aerogel is so light, this insulation doesn't come with the weight penalty you might expect. You're not wrapped in heavy, bulky layers that restrict movement. Instead, you have a thin, lightweight barrier that performs better than materials many times thicker and heavier. The inverse of this cryogenic protection is equally impressive, and perhaps even more startling to witness. You can handle extremely hot objects through aerogel without feeling heat. Picture this scenario: a blowtorch flame, burning at perhaps 1,300 degrees Celsius, focused on one side of a thin aerogel tile. The tile might be only a centimeter or two thick. On the other side, someone places their hand, palm flat against the surface. What happens? Remarkably, almost nothing happens. The person feels a little warmth, perhaps, but nothing painful, nothing concerning. The aerogel is performing its function, creating such resistance to heat flow that even a blowtorch flame on one side produces only mild warming on the other. The temperature gradient across this thin material is enormous, from over 1,000 degrees on one side to perhaps 30 or 40 degrees on the other. The aerogel maintains this gradient through the same mechanisms we've discussed. Minimal solid conduction, disrupted gas conduction, impossible convection. The heat cannot find an easy path through. This demonstration has become something of a signature showcase for aerogel's capabilities. It's visceral, dramatic, immediately comprehensible. Fire is dangerous. We all know this intuitively from our earliest experiences. We learn as children not to touch hot things, to respect flames. And here is a material that seems to violate this fundamental caution, allowing you to safely touch something that should burn you instantly. It's not magic, of course. It's physics, it's structure, it's the careful engineering of matter at the nanoscale. But the effect is undeniably remarkable. What makes these demonstrations of extreme temperature resistance particularly noteworthy is that aerogels maintain insulation where ordinary materials fail at extremes. Many conventional insulators lose their effectiveness at very high or very low temperatures. Some materials become brittle and crack in extreme cold. Others decompose, melt, or catch fire at high temperatures. Many materials that insulate well at room temperature see their thermal conductivity increase dramatically when subjected to temperature extremes, as new heat transfer mechanisms become dominant or as the material's structure changes. Aerogel, by contrast, maintains its basic structural integrity and insulating properties across an enormous temperature range. The nanoscale network of struts doesn't fundamentally change just because the temperature shifts. The pores remain the same size. The mechanisms that suppress heat transfer continue to operate. This stability across temperature extremes is rare and valuable, making aerogel suitable for applications where the temperature might vary wildly or reach extremes that would destroy conventional materials. However, aerogel's story at extreme temperatures isn't quite as simple as it works everywhere always. There are challenges, particularly at very high temperatures, that require understanding and mitigation. At higher temperatures, radiative heat transfer becomes dominant. We've talked extensively about conduction through solids and gases, and about convection in fluids. But there's a fourth way that heat can transfer: radiation. All objects emit thermal radiation, electromagnetic waves, primarily in the infrared spectrum, based on their temperature. The hotter something is, the more radiation it emits, and the intensity increases rapidly with temperature, following the Stefan-Boltzmann law, which states that radiated power increases with the fourth power of absolute temperature. Double the absolute temperature, and the radiated power increases by a factor of 16. At room temperature, thermal radiation is a relatively minor contributor to heat transfer. Conduction and convection usually dominate. But at higher temperatures, particularly above several hundred degrees Celsius, radiation becomes increasingly important. And here's where aerogel encounters a challenge. Many aerogels, particularly silica aerogels, are relatively transparent to infrared radiation. This near-infrared transparency can cause thermal conductivity to rise at high temperatures. The infrared radiation passes through the aerogel structure much more easily than heat trying to conduct through the material. The photons carrying thermal energy don't need to navigate the tortuous path through the solid network. They don't collide with pore walls. They simply travel in straight lines through the material, carrying energy from the hot side to the cool side. As temperature increases and radiation becomes more intense, this transparency to infrared allows heat to bypass the mechanisms that make aerogel such an effective insulator at lower temperatures. For applications at very high temperatures, this is a problem. A material that insulates beautifully at a few hundred degrees might perform disappointingly at 1,000 degrees if radiation can pass through unimpeded. The effective thermal conductivity, which includes all mechanisms of heat transfer, not just conduction, rises as radiative transfer dominates. The aerogel is still suppressing conduction admirably, but that's no longer the main story. Radiation has taken over. Fortunately, this challenge has a solution. Infrared blocking additives dramatically improve high-temperature performance. By incorporating materials that absorb or scatter infrared radiation into the aerogel structure, researchers can create aerogels that remain opaque to thermal radiation, even at high temperatures. These additives might be tiny particles of carbon, silicon carbide, titanium dioxide, or other materials that interact strongly with infrared light. They're dispersed throughout the aerogel structure, creating obstacles for infrared photons trying to pass through. When infrared radiation encounters these particles, it gets absorbed and re-emitted in random directions, or it gets scattered, changing direction multiple times as it tries to traverse the material. Either way, the straight-line path through the aerogel is blocked. The radiation can still eventually make it through, but the process is much slower, much less efficient. The additives have created a barrier to radiative heat transfer, complementing aerogel's existing barriers to conductive and convective transfer. The result of this innovation is that advanced aerogels remain effective up to 1,200 to 1,500 degrees Celsius. This is an extraordinary temperature range. To put it in perspective, aluminum melts at about 660 degrees Celsius. Steel melts around 1,500 degrees Celsius, depending on the alloy. These advanced aerogels can maintain their insulating properties at temperatures where many metals would be liquid, where most organic materials have long since burned away, where the environment would appear to glow with its own heat. At 1,500 degrees Celsius, you're approaching the temperature of some industrial furnaces, of certain stages of combustion engines, of materials processing operations. You're well into the range where conventional insulators fail, where options become limited and expensive. And yet these advanced aerogels continue to function, continue to resist heat flow, continue to maintain temperature gradients that would be impossible with traditional materials. This high-temperature capability makes aerogels suitable for aerospace and hypersonic environments. Consider the challenges faced by vehicles traveling at hypersonic speeds, 5 times the speed of sound or faster. At these velocities, air friction generates enormous heat. The surface of a hypersonic vehicle can reach temperatures exceeding 1,500 degrees Celsius, hot enough to glow visibly. The structure underneath must be protected from this heat, but the protection must also be lightweight, because every kilogram of weight on a spacecraft or high-speed aircraft represents a significant penalty in fuel requirements and performance. Aerogel offers a solution. Its extreme lightness means that even a substantial layer adds minimal weight to the vehicle. Its thermal insulation properties mean that this lightweight layer can protect sensitive internal components from the searing heat of atmospheric re-entry or hypersonic flight. And its stability at high temperatures means it won't decompose, melt, or fail when exposed to the conditions it's designed to protect against. NASA has recognized this potential and has incorporated aerogel into various spacecraft applications. Beyond just insulation, aerogel has been used in particle capture systems. Its vast internal surface area and delicate structure make it ideal for catching microscopic particles without destroying them. The Stardust mission, which collected samples from a comet's tail and returned them to Earth, used aerogel as a capture medium. When tiny particles hit the aerogel at high speeds, they burrowed into the structure, creating carrot-shaped tracks, but remaining intact for later analysis. No other material could have accomplished this feat. Something hard would have vaporized the particles on impact, while something too soft wouldn't have stopped them. But returning to thermal applications, consider future hypersonic aircraft. Vehicles designed to travel at several times the speed of sound for extended periods. These vehicles face sustained heating, not just the brief pulse of heat during re-entry that spacecraft experience. The thermal protection system must work for hours, not minutes, and it must do so while remaining as light as possible to allow the vehicle to achieve and maintain hypersonic speeds. Advanced aerogels, with their infrared blocking additives and high-temperature stability, represent one of the most promising solutions to this engineering challenge. They provide the necessary thermal protection without the weight penalty that would make such vehicles impractical. They maintain their properties across the temperature range the vehicle will experience, from the cold of high altitude to the heat of hypersonic flight. And they can be manufactured in forms, tiles, blankets, panels, that can be integrated into complex vehicle geometries. As we contemplate aerogel protecting spacecraft during re-entry or insulating hypersonic vehicles traveling at the edge of what's possible, we're seeing the culmination of that nanoscale engineering we discussed earlier. The careful structuring of matter at scales measured in tens of nanometers creates properties that enable technologies at the grandest scales. Vehicles traveling thousands of kilometers per hour, missions to other worlds, the expansion of human presence beyond Earth. There's something profound in this connection between the very small and the very large, between the invisible architecture of aerogel's pores and the visible trajectory of a spacecraft returning from orbit. The same material that can protect your hand from a blowtorch in a laboratory demonstration can protect an entire vehicle from the fury of atmospheric friction at hypersonic speeds. The principles don't change, only the scale of application. And yet, for all of aerogel's remarkable thermal properties, for all its capability at temperature extremes, this is just one aspect of what makes the material so fascinating. In our next segment, we'll explore the history of aerogel's discovery, the challenges faced in developing it, and the various forms this material can take beyond silica. But for now, rest with this image. A thin layer of nearly invisible material, standing between extreme heat and extreme cold, maintaining gradients that seem impossible, protecting through structure rather than mass, achieving through emptiness what dense materials cannot achieve through substance. This is aerogel as thermal guardian, light as air, yet more effective than materials many times heavier, a testament to what becomes possible when we learn to engineer at the scale where matter begins. When we think about the strength of materials, we often think in absolutes. Steel is strong, glass is brittle, rubber is elastic, but aerogel, as we've come to expect by now, doesn't fit neatly into these simple categories. Its mechanical behavior is nuanced, complex, and deeply tied to its nanoscale structure. To understand how aerogel responds to force, we need to move beyond simple labels and explore the subtle ways that a material made mostly of emptiness can bear loads, compress, stretch, and sometimes fail. Aerogels are brittle under sharp impact, but elastic under gentle compression. This dual nature is one of the first things you notice if you handle aerogel. Tap it sharply with a hard object, and it may crack or crumble. The material doesn't tolerate sudden, concentrated forces well. It's fragile in the way that a dry cracker is fragile, or how certain foams shatter when struck. There's a brittleness to it, a sense that it could break if you're not careful. But press on it gently with your finger, and something different happens. The aerogel compresses slightly under the pressure. You can feel it give just a little. Release the pressure, and it springs back, recovering much of its original shape. This elasticity seems at odds with the brittleness. How can something be both fragile and springy, both prone to cracking and capable of recovering from compression? The answer lies in understanding what actually happens at the nanoscale when aerogel deforms. Deformation occurs through bending of nanostruts rather than bulk crushing. Remember that aerogel consists of a network of incredibly thin solid struts connected at nodes, creating a continuous framework suspended in air. When you apply gentle, distributed pressure to aerogel, you're not crushing this network in the way you might crush a solid block of material. Instead, you're causing those individual nanostruts to bend slightly. Imagine a bridge made of metal girders. If you load the bridge gradually and evenly, the girders flex slightly under the load. Each one bends a tiny amount, and the structure as a whole accommodates the load through these small deflections. As long as you don't exceed the elastic limit of the girders, they'll spring back to their original shape when the load is removed. This is essentially what happens in aerogel under gentle compression. The nanostruts bend elastically, the structure compresses slightly, and when you release the pressure, the struts straighten back out. But what about that brittleness under sharp impact? When you strike aerogel suddenly with a hard object, you're applying force in a concentrated way that doesn't distribute evenly through the structure. The struts near the impact point must absorb a large amount of energy very quickly. Some struts bend beyond their elastic limit and break. Once struts break, the network loses continuity in that region. The fracture propagates as neighboring struts become overloaded by the sudden redistribution of forces. The result is a crack or a crumbling failure, brittleness. So aerogel isn't simply brittle or simply elastic. It's both, depending on how the force is applied. This is actually true of many materials, but in aerogel the contrast is particularly striking because the material looks so delicate that you might expect it to shatter at the slightest touch. Yet it can also be surprisingly resilient under the right conditions. The mechanical properties of aerogels have improved dramatically as researchers have learned to engineer their structure more precisely. Early aerogels were extremely fragile, beautiful curiosities, but not suitable for most practical applications where materials must withstand handling and use. But newer formulations and structures have changed this picture considerably. Graphene aerogels can recover after compressive strains up to about 80%. This is remarkable. Compressive strain is the amount of deformation relative to the original size. An 80% compressive strain means you've compressed the material to just 20% of its original thickness. You've squeezed it down to 1/5 of its starting size. For most aerogels, this would cause permanent deformation or complete collapse. But graphene aerogels, made from interconnected sheets and ribbons of graphene, the single atom-thick form of carbon, can be compressed this much and then spring back nearly to their original shape. This extraordinary recovery comes from graphene's own remarkable mechanical properties. Graphene is one of the strongest materials known per unit weight. A single sheet of graphene is incredibly difficult to break or stretch. When these sheets are assembled into an aerogel structure, they create a network that's both lightweight and resilient. The graphene sheets can bend and fold under compression without breaking, and the structure can absorb enormous deformations without losing its connectivity. Imagine crushing a structure made of paper-thin metal sheets arranged in a complex three-dimensional network. The sheets bend and fold, the structure compresses dramatically, but as long as the sheets don't tear and the connections don't break, the whole thing can potentially unfold back to something close to its original shape. This is what happens in graphene aerogels. The atomic scale thickness and strength of graphene allows for this remarkable reversibility. This resilience opens up applications where earlier aerogels would have been impractical. Imagine an aerogel used as cushioning or shock absorption, where it needs to compress and recover repeatedly. Or consider aerogels used in environments where they might accidentally be compressed, perhaps in clothing or in equipment that might get packed tightly for transport. Graphene aerogels can survive these insults and continue functioning. But it's not just about compression. Researchers have also worked to improve other mechanical properties. Some designs reach Young's moduli above 300 kilopascals despite ultra-low density. Young's modulus is a measure of a material's stiffness, how much force is required to deform it by a given amount. A high Young's modulus means the material is stiff and resists deformation. A low Young's modulus means it's easily deformed. For context, rubber has a Young's modulus of around 1 to 10 megapascals. Aluminum is around 70 gigapascals. 300 kilopascals, which is 0.3 megapascals, might not sound impressive compared to metals or even to rubber. But remember, we're talking about materials with densities as low as 0.001 grams per cubic centimeter, materials that are more than 99% air. For something that weighs almost nothing, achieving any significant stiffness is remarkable. The achievement here is about efficiency, getting mechanical performance from minimal material. If you need a lightweight structure that still maintains some rigidity, these engineered aerogels offer a combination of properties that's difficult to match. They won't be as stiff as solid materials, but they're far stiffer than you'd expect from their weight. And in applications where every gram matters, this efficiency is valuable. Researchers have also tackled the problem of tensile strength. resistance to being pulled apart. Carbon nanotube reinforced aerogels can stretch over 40% before fracture. Pure silica aerogels are quite weak in tension. Pull on them, and they'll tear or break fairly easily. But by incorporating carbon nanotubes, cylindrical molecules of carbon with extraordinary tensile strength, into the aerogel structure, researchers have created hybrid materials that can withstand substantial stretching. 40% elongation before fracture means you can pull the material to 1.4 times its original length before it breaks. This is far more than traditional aerogels could ever achieve. The carbon nanotubes act as reinforcement, similar to how steel rebar reinforces concrete, or how fibers reinforce composite materials. When the aerogel is stretched, the nanotubes bear much of the tensile load, preventing the failure that would otherwise occur in the silica or carbon framework alone. This ability to stretch without immediate failure makes these reinforced aerogels suitable for applications where flexibility is needed, perhaps as components in flexible devices, or in situations where the material might need to conform to curved surfaces or accommodate movement without cracking. Durability over repeated use is another important consideration. It's one thing for a material to survive a single compression or deformation. It's quite another for it to survive hundreds or thousands of cycles. Ceramic fibrous aerogels survive hundreds of loading cycles. These aerogels, made from ceramic fibers arranged in an aerogel-like structure, can be compressed and released hundreds of times without significant degradation of their properties. This cyclic durability is crucial for any application where the material will be used repeatedly rather than just once. Think of insulation that might be compressed during installation and then needs to maintain its properties for years. Or consider acoustic damping applications where the material experiences continuous vibration. Or thermal insulation that undergoes repeated thermal cycling, expanding and contracting as temperatures change. Materials that fail after just a few cycles are unsuitable for these applications. But ceramic fibrous aerogels demonstrate that aerogel structures can be engineered for long-term reliability. Researchers have also explored more unconventional structural approaches. Pre-stressed knitted frameworks increase tensile strength above 350 kilopascals. This approach involves creating aerogel structures with a knitted architecture, interlocking loops and connections, similar to knitted fabric, but at a much smaller scale. By pre-stressing this framework, applying controlled tension during formation, the resulting aerogel has improved tensile properties. The knitted architecture distributes loads differently than a random network would. When you pull on a knitted structure, the load is carried through the interlocking connections in a more organized way. The pre-stressing ensures that the structure is already under some tension, which can prevent slack regions that would otherwise allow deformation before load bearing begins. The result is an aerogel with tensile strength that rivals or exceeds its compressive strength, an unusual and valuable property. Speaking of unusual mechanical behaviors, some aerogels adapt mechanically by redistributing stress. This is a fascinating emergent property of certain aerogel architectures. When you apply force to these materials, they don't just deform passively according to their structure. Instead, the way load is distributed through the network changes in response to the deformation itself. Struts that were carrying little load become more engaged. Regions that were being overstressed partially unload as the deformation allows alternative load paths to develop. This adaptive behavior is somewhat similar to how a group of people carrying a heavy object might naturally adjust their positions and grips to balance the load more comfortably. The aerogel structure, through its complex network of connections, finds more efficient ways to carry the applied load as it deforms. This can make the material tougher and more resilient than its initial structure would suggest, because it's not locked into a single load distribution pattern. The mechanical properties can also vary depending on the direction of applied force. In some silica aerogels, shear strength exceeds tensile strength. Shear strength is resistance to sliding forces. Imagine trying to slide two layers of the material past each other, like sliding cards in a deck. Tensile strength is resistance to being pulled apart. Normally, we might expect these to be similar, or for tensile strength to be higher. But in some aerogels, the structure is better at resisting shear than tension. This happens because of how the nanoscale network responds to different types of force. When you pull on the aerogel in tension, you're asking struts to resist being stretched and pulled apart. Some struts may be oriented poorly for this and carry little load, while others become overstressed. But when you apply shear forces, you're asking the structure to resist a different type of deformation, twisting and sliding. The network's connectivity and the way struts are bonded at nodes may make it more effective at resisting this shear deformation. This directional dependence in strength is another reminder that mechanical behavior strongly depends on internal architecture. You can have two aerogels with the same composition, the same density, the same thermal properties, but if their internal structures differ, if one has longer struts with fewer connections while the other has shorter struts with more connections, or if one has a more ordered arrangement while the other is more random, their mechanical properties can be dramatically different. This structure-property relationship is both a challenge and an opportunity. It's a challenge because you can't simply specify aerogel and expect consistent mechanical performance. You need to carefully control the synthesis process to create the internal architecture you need for your application. But it's also an opportunity because it means that by engineering the structure, controlling pore size, strut thickness, connectivity, perhaps incorporating reinforcements or creating organized architectures, you can tune the mechanical properties to meet specific requirements. Some aerogels are designed to be as stiff as possible for structural applications. Others are designed to be compressible and elastic for cushioning or insulation that must tolerate handling. Still others are designed to be strong in specific directions or to have particular combinations of properties. The structure can be tailored, at least within limits, to achieve desired outcomes. As you hold a piece of aerogel in your hand, all of this complexity is present but invisible. You feel the lightness, the slight give when you press gently, the sense that it might break if you're too rough. But you're not feeling the material itself so much as you're feeling the consequences of its structure. The way those billions of nanostruts bend and flex, the way forces distribute through a network that's mostly empty space, the way architecture at the scale of viruses determines behavior at the scale of your fingers. This hidden complexity, this deep connection between nanoscale structure and macroscale properties, is what makes aerogel such a rich subject for research and engineering. Every improvement in mechanical properties represents a success in controlling structure at scales we can't directly see. Every new formulation that makes aerogel stronger, more flexible, more durable, or more resilient represents our growing ability to design matter from the bottom up, to specify not just what something is made of, but exactly how it's put together. In our next segment, we'll journey back in time to explore how aerogel was discovered, the challenges early researchers faced, and the evolution of aerogel science over the decades. But for now, consider the paradox of mechanical behavior in a material made mostly of nothing. Brittle yet elastic, fragile yet capable of supporting thousands of times its own weight, seemingly delicate yet increasingly engineered for durability. This is aerogel as structural material, as bearer of loads, as substance that achieves through architecture what denser materials achieve through mass. And in that achievement, we see the power of structure itself, the proof that how you arrange atoms can matter as much as which atoms you use. Every remarkable material has an origin story, a moment when someone first wondered, what if? And then pursued that question into unknown territory. For aerogel, that moment came during the Great Depression, in a time when the world seemed focused on immediate survival rather than scientific curiosities. Yet it was precisely then, in 1931, that a scientist named Samuel Kistler would create something that wouldn't find widespread application for decades, but would eventually prove to be one of the most extraordinary materials humanity has ever synthesized. Aerogel was invented in 1931 by Samuel Kistler. Kistler was working at the College of the Pacific in California, and like many scientists, he was driven by curiosity about a specific question. He was interested in gels, those strange substances that are part liquid, part solid, with properties of both. Gelatin desserts are gels. So is the material in silica packets that keep electronics dry. Gels have a solid network that gives them structure, but most of their volume is actually liquid trapped within that network. Kistler wondered about something that might seem simple at first. What would happen if you could remove all the liquid from a gel without allowing the solid network to collapse? What would remain? Would you have a solid with the same volume as the original gel, just without the liquid? Or would the structure crumble without the liquid to support it? The original challenge was replacing a gel's liquid with gas without collapse. This turns out to be extraordinarily difficult. If you simply let a gel dry naturally, leaving it out in air so the liquid evaporates, something unfortunate happens. As the liquid evaporates from the surface, it creates an interface between the remaining liquid and the air. This interface has surface tension, the same force that allows water striders to walk on water and causes water to bead up on a wax surface. Surface tension creates pressure. In the tiny pores of a gel, where the scale is measured in nanometers, this pressure becomes enormous. As the liquid recedes during drying, the surface tension pulls inward on the solid network with tremendous force. The delicate struts and connections of the gel cannot resist this force. They bend inward, collapse toward each other, and the structure shrinks dramatically. By the time all the liquid has evaporated, what remains is a dense, shrunken solid, perhaps just a few % of the original gel's volume. The open structure, the vast internal porosity, all of that has been crushed by the forces generated during drying. This collapse is why ordinary drying doesn't work for creating aerogel. You'd start with a gel that's 99% liquid by volume, and you'd end up with a dense solid that's nothing like the airy structure you wanted. The challenge, then, was to find a way to remove the liquid without ever allowing those destructive surface tension forces to develop. Kistler's insight was that supercritical drying made this possible. To understand this solution, we need to briefly discuss the states of matter and what happens at the critical point. We're all familiar with solids, liquids, and gases. Water ice is solid, liquid water is liquid, and water vapor is gas. You can change from one to another by adjusting temperature and pressure. Normally, when a liquid becomes a gas, there's a clear boundary, the surface of the liquid where it meets the air. This boundary is where surface tension acts. But there's a special combination of temperature and pressure called the critical point. Beyond the critical point, the distinction between liquid and gas disappears. The substance enters what's called a supercritical state. It has properties of both liquid and gas, but it's neither one definitively. And crucially, a supercritical fluid has no surface. There's no interface, no boundary where surface tension can act. Kistler realized that if he could heat a gel under pressure until the liquid within it went supercritical, and then carefully vent away this supercritical fluid, the gel structure wouldn't experience the destructive surface tension forces of ordinary drying. The supercritical fluid would simply diffuse away, leaving the solid network intact. This avoids surface tension forces that destroy delicate structures. The process works like this. You start with a gel saturated with liquid, typically alcohol rather than water, because alcohol has a lower critical point and is easier to work with. You place this gel in a pressure vessel, a strong container that can withstand high pressures. You heat the vessel, raising both temperature and pressure. The liquid alcohol in the gel's pores reaches its critical point, about 240 degrees Celsius and 63 atmospheres of pressure for ethanol. At this point, you're now dealing with supercritical alcohol throughout the gel structure. Then, very carefully, you begin to release the supercritical fluid from the vessel. You must do this slowly, maintaining conditions above the critical point throughout the venting process, never allowing the supercritical fluid to condense back into a liquid. As the supercritical alcohol escapes, it's replaced by ordinary gas, initially carbon dioxide or nitrogen, eventually just air. The gel's structure remains supported throughout this transition because there's never a liquid-gas interface, never a surface tension force pulling it inward. Finally, when all the supercritical fluid has been removed and replaced with gas, you cool the vessel and release the pressure. What remains is aerogel, the solid network of the original gel, now filled with air instead of liquid, retaining nearly all of the original gel's volume. Aerogels are produced by drying wet gels beyond the critical point. This single sentence describes the process that makes aerogel possible, the crucial insight that Kistler had nearly a century ago. Kistler's first aerogels were silica-based, created from silica gels similar to those used as desiccants. The results were remarkable, ghostly, blue-tinted solids that weighed almost nothing yet maintained their shape. He published his findings, and the scientific community was intrigued. Here was a material with properties unlike anything seen before. Extraordinary lightness combined with solidity, a material that was mostly air yet clearly structured. But intrigue didn't immediately translate to practical application. Early production methods were slow and expensive. The supercritical drying process required specialized pressure vessels capable of withstanding high temperatures and pressures. Each batch took hours, or even days to complete. The chemicals needed were costly. The process required careful monitoring and control. For decades after Kistler's discovery, aerogel remained primarily a laboratory curiosity. Fascinating to scientists, useful for very specialized applications where cost was secondary, but far too expensive and difficult to produce for any widespread use. The equipment itself was a barrier to scaling up production. Pressure vessels that can safely handle supercritical conditions aren't simple to manufacture or operate. They require thick walls to contain the pressure, careful temperature control, and safety systems to prevent dangerous failures. Building larger vessels to process more material at once helped somewhat, but the fundamental economics of the process remained challenging. You were using significant energy to heat materials to supercritical conditions, maintaining those conditions for extended periods, and doing all of this in expensive equipment. For many years, if you wanted aerogel, you either made it yourself in a laboratory setting, producing small quantities for research, or you paid a premium to one of the few suppliers who offered it commercially. This limited aerogel's applications to situations where its unique properties justified the high cost. Specialized scientific instruments, certain aerospace applications, demonstrations, and research. The broader potential of the material remained largely untapped simply because it was too expensive and too difficult to produce in quantity. But as with many technologies, persistent research and development gradually transformed this picture. In recent decades, ambient pressure drying techniques are now emerging. These methods represent a fundamental change in approach. Instead of requiring supercritical conditions, high temperatures and high pressures, these new techniques find ways to strengthen the gel structure so it can withstand ordinary drying, or they modify the surface chemistry to reduce surface tension forces, or they use solvents with lower surface tension than water. One approach involves treating the gel's surface with chemicals that make it hydrophobic, water-repelling. This surface modification changes how the liquid interacts with the solid network during drying. The surface tension forces are still present, but they act differently on the modified surface, often pulling less strongly on the structure. Combined with careful control of the drying conditions, perhaps using solvents that evaporate more slowly or have lower surface tension, it becomes possible to dry gels at ambient pressure without complete collapse. These ambient pressure methods don't always produce aerogels with properties quite as exceptional as those made through supercritical drying. The density might be somewhat higher, the pores might be somewhat less uniform. But the trade-off can be worthwhile if it means you can manufacture aerogel without expensive pressure vessels, without the energy costs of reaching supercritical conditions, without the lengthy processing times. For many applications, a slightly less perfect aerogel that costs a fraction of the price is far more useful than an ideal aerogel that's prohibitively expensive. Alongside these new drying methods, continuous manufacturing methods reduce costs significantly. Early aerogel production was a batch process. You made one batch, waited for it to complete, removed the product, started the next batch. But continuous manufacturing allows you to feed material into one end of a process and retrieve finished product from the other end in an ongoing flow. This is far more efficient, reducing the time equipment sits idle and allowing for economy of scale. Continuous processes for aerogel might involve creating the initial gel in a continuous flow, perhaps extruding it or forming it on a moving belt. The gel then moves through treatment stages, eventually reaching a drying section where liquid is removed through whatever method is being used. The finished aerogel emerges continuously and can be collected, cut to size, and packaged. The entire process might take hours from start to finish, but because it's continuous, you're producing aerogel constantly rather than in discrete batches separated by waiting periods. This shift to continuous manufacturing has been crucial in making aerogel economically viable for more applications. When you can produce aerogel in large quantities efficiently, the cost per unit drops dramatically. What was once a specialty material costing hundreds or thousands of dollars per kilogram can potentially become something costing tens of dollars per kilogram. Still expensive compared to conventional insulation, but reasonable for applications where aerogel's unique properties provide significant value. The evolution of manufacturing methods has also enabled new possibilities in how aerogel can be formed and shaped. Additive manufacturing allows complex aerogel geometries. Additive manufacturing, commonly known as 3D printing, builds objects layer by layer according to a digital design. Applying this approach to aerogels opens up remarkable possibilities. Traditional aerogel manufacturing produces relatively simple shapes: blocks, sheets, cylinders, perhaps simple molded forms. But what if you needed aerogel in a complex shape tailored to a specific application? What if you wanted to create an aerogel structure with varying density in different regions, or with internal channels for fluid flow, or with intricate geometric patterns that enhance particular properties? Additive manufacturing makes these things possible. The process might involve printing a gel ink layer by layer, allowing it to set into a three-dimensional structure, and then drying this structure using supercritical or ambient pressure methods. Or it might involve printing a template or scaffold that guides gel formation. The details vary depending on the specific approach, but the result is the same. You can create aerogel components with geometries that would be impossible to produce through traditional methods. This capability is particularly valuable in research settings, where scientists want to explore how different structures affect aerogel properties. It's also useful for creating custom components for specialized applications. Perhaps an aerogel thermal insulator shaped precisely to fit around a particular piece of equipment, or an aerogel acoustic dampener designed with internal structures optimized for absorbing specific frequencies of sound. The cumulative effect of all these advances, ambient pressure drying, continuous manufacturing, additive manufacturing, and numerous other improvements in chemistry and processing, is that aerogels have transitioned from lab curiosities to scalable materials. This transition has been gradual, occurring over decades, but it represents a fundamental shift in aerogel's place in the world of materials. In Kistler's time, aerogel was a remarkable demonstration of what was possible, but with no clear path to practical use. By the late 20th century, aerogel was being used in specialized applications: NASA missions, high-end windows, scientific instruments, but still in relatively small quantities at high cost. Now, in the 21st century, we're seeing aerogel appear in consumer products, in industrial insulation, in construction materials. It's still not as common as fiberglass or foam, but it's no longer a rarity accessible only to researchers with specialized equipment and budgets. This journey from laboratory curiosity to scalable material mirrors the path many advanced materials have taken. Often, the initial discovery comes from pure scientific inquiry, someone asking a question simply because they want to know the answer. The material's properties are explored and documented, but applications remain limited because production is difficult or expensive. Then, gradually, as researchers develop better manufacturing methods, as economies of scale begin to apply, as new applications are identified that can justify even moderate costs, the material begins to transition into broader use. Aerogel is currently somewhere in the middle of this transition. It's no longer exotic, but neither is it commonplace. You can purchase aerogel insulation for your home, but it costs significantly more than conventional insulation, so most people don't. You can buy aerogel insulated clothing, but it's a premium product. Industries use aerogel where its unique properties, extreme lightness, exceptional insulation, high temperature stability, provide enough value to justify the cost, but they don't use it where conventional materials would work fine. As manufacturing continues to improve and costs continue to decline, we'll likely see aerogel move further into the mainstream. Perhaps in a few decades, aerogel insulation will be common in buildings, chosen not just for its performance, but because its cost has become competitive with alternatives when you account for its superior properties, allowing thinner walls and more usable space. Perhaps aerogel will become standard in certain types of clothing, packaging, or industrial equipment. But even if aerogel never becomes truly commonplace, its journey from Kistler's laboratory in 1931 to today's commercial products is a testament to the long arc of materials science. It took nearly 50 years from Kistler's discovery before NASA began using aerogel in space applications. It took another few decades before commercial aerogel products became available to consumers. Each step required solving technical challenges, developing new processes, finding applications that could justify the cost, building manufacturing infrastructure. Samuel Kistler, working in his laboratory nearly a century ago, was simply trying to answer a question about gels. He probably couldn't have imagined that his supercritical drying process would eventually lead to materials protecting spacecraft during re-entry, insulating homes, capturing particles from comets, or being incorporated into clothing for extreme environments. But that's often how scientific discovery works. Someone explores a question out of curiosity, develops a method to answer that question, and creates something whose ultimate value and applications only become clear decades later. As we consider aerogel's history, we're reminded that materials science is a cumulative endeavor. Kistler provided the crucial insight about supercritical drying. Subsequent researchers explored different gel chemistries, creating aerogels from various materials. Others developed new applications, demonstrating aerogel's value in specific contexts. Still others worked on manufacturing challenges, finding ways to make production faster, cheaper, more reliable. Each contribution built on what came before, gradually transforming aerogel from an interesting oddity into a practical material. In our next segment, we'll explore the different types of aerogels beyond silica, the organic, carbon, metal oxide, and composite varieties that extend aerogel's properties in new directions. But for now, rest with the image of that first aerogel, created through careful control of temperature and pressure, emerging from Kistler's apparatus as something the world had never seen before. Frozen smoke, solid air, a material that challenged assumptions about what was possible. That moment of creation, that first success in replacing liquid with gas without collapse, opened a door to a new category of materials. And we're still exploring what lies beyond that door, still discovering new possibilities in structures made mostly of emptiness. When we've spoken about aerogel so far, we've focused primarily on silica aerogel, the original form, the frozen smoke that first emerged from Samuel Kistler's laboratory. But the genius of the aerogel concept extends far beyond silica. The fundamental idea, creating a nanoscale network of solid material through supercritical drying or related techniques, can be applied to many different materials. And when you change the chemistry while maintaining the structure, you unlock entirely new sets of properties and applications. Aerogels can be made from silica, carbon, alumina, titania, cellulose, and more. Each of these materials brings its own characteristics to the aerogel structure. Silica aerogels, as we've discussed extensively, are excellent thermal insulators with low density and reasonable mechanical properties. They're transparent or translucent, they have that characteristic blue haze, and they're chemically fairly inert. But silica doesn't conduct electricity. It's an insulator in both the thermal and electrical sense. For many applications, this is perfectly fine. But what if you wanted an aerogel that could conduct electricity? For that, you'd need a different material. Carbon aerogels can be electrically conductive. These aerogels are made from carbon rather than silica, and carbon's electronic properties are fundamentally different. Depending on how carbon atoms are arranged, carbon can be highly conductive. Think of graphite, which conducts electricity well enough to be used in batteries and electrical contacts. When you create an aerogel structure from carbon, you get a material that retains the aerogel's characteristic low density and high porosity, but now with the ability to conduct electricity through its structure. Carbon aerogels are typically created by starting with an organic polymer gel, perhaps resorcinol formaldehyde, a common precursor, and then heating this gel in an inert atmosphere to high temperatures, around 800 to 1000 degrees Celsius or higher. This process, called pyrolysis, drives off most of the non-carbon elements, hydrogen, oxygen, nitrogen, leaving behind a structure that's predominantly carbon. The result is a black, electrically conductive aerogel with properties quite different from silica. These conductive aerogels have found applications in energy storage. Battery electrodes need to be conductive, and they benefit from high surface area to allow more sites for electrochemical reactions. Carbon aerogels provide both conductivity from the carbon itself and enormous surface area from the aerogel structure. They've been used in supercapacitors, devices that can store and release electrical energy very quickly. They've been explored for fuel cell components, where their conductivity and porosity allow efficient transport of both electrons and reactant gases. But carbon aerogels can offer even more unusual properties. Graphene aerogels can generate sound directly from light. This is a truly remarkable phenomenon that seems almost magical when you first encounter it. Shine a modulated light source, perhaps a pulsed laser or an LED that's being rapidly turned on and off, onto a graphene aerogel, and the aerogel produces sound. The light itself makes no sound, of course, but the aerogel, responding to the light, becomes a speaker. The mechanism behind this photoacoustic effect is based on rapid heating and cooling. When light hits the graphene aerogel, the material absorbs the light's energy and converts it to heat almost instantaneously. This sudden heating causes the aerogel and the surrounding air to expand rapidly. When the light turns off, the material cools quickly and contracts. If you modulate the light at audio frequencies, 20 to 20,000 times per second, these rapid expansions and contractions create pressure waves in the air, sound. Graphene is particularly effective for this because it has very low heat capacity. It doesn't take much energy to change its temperature, and because it can heat and cool very rapidly. The aerogel structure is important too, because the large surface area and intimate contact with air allow efficient transfer of these temperature changes to the surrounding atmosphere. Lower density improves photothermoacoustic efficiency. The less material there is, the less energy is needed to heat it, and the faster it can respond to changes in illumination. Ultra-low density graphene aerogels, therefore, make particularly efficient photoacoustic transducers. This might seem like a novelty, but it has potential applications. Imagine speakers with no moving parts, no diaphragms or voice coils, just a thin layer of aerogel that produces sound when illuminated with modulated light. Such speakers could be extremely thin, flexible, and resistant to damage since there's no delicate mechanical components to break. They might be incorporated into transparent displays, creating sound that seems to emerge from nowhere. Or they could be used in environments where traditional speakers would fail. In vacuum chambers, for instance, where you could shine modulated light through a window onto aerogel inside, generating sound without needing electrical connections through the vacuum seal. Moving beyond carbon, we encounter aerogels made from entirely different classes of materials. Metal oxide aerogels, alumina, titania, zirconia, and others, bring the properties of these materials to the aerogel structure. Alumina aerogel, for instance, combines low thermal conductivity with exceptional stability at high temperatures, even beyond what silica can achieve. Titania aerogel has photocatalytic properties. It can use light energy to drive chemical reactions, breaking down pollutants or splitting water molecules. These metal oxide aerogels expand aerogel's application space considerably. Alumina aerogels might be used in ultra-high temperature furnace insulation, where even advanced silica aerogels would eventually soften or fail. Titania aerogels could be incorporated into self-cleaning surfaces or air purification systems, using their large surface area to maximize their photocatalytic effect. Each material brings its own chemical and physical properties, and the aerogel structure amplifies the utility of those properties by maximizing surface area while minimizing weight. One particularly exciting development involves MOF aerogels, which combine micro and macroporosity. MOF stands for Metal Organic Framework, a class of materials made from metal ions connected by organic molecules into highly ordered crystalline structures. MOFs are famous for having enormous surface areas, some exceed 7,000 square meters per gram, and for having very uniform, precisely sized pores at the molecular scale, typically less than 2 nanometers across. By creating aerogels from MOFs, researchers achieve a hierarchical pore structure. The MOF material itself has micropores, the tiny, molecular-scale pores within the crystalline framework. But the aerogel structure creates macropores, larger pores, tens or hundreds of nanometers across, between the MOF particles or crystals. This hierarchy of pore sizes is extremely valuable because different transport and reaction processes favor different pore sizes. Hierarchical pores enhance catalysis and gas separation. In catalysis, chemical reactions often occur at active sites on a surface. If all your pores are micropores, reactant molecules can reach these active sites, but the diffusion through such small pores is slow. Molecules bump into walls constantly, making their journey tortuous and time-consuming. If all your pores are macropores, molecules can move quickly, but you don't have as much surface area or as many active sites. But with hierarchical porosity, you get the best of both worlds. Large macropores that allow rapid transport of molecules to the general vicinity of active sites, and micropores that provide enormous surface area and precisely sized environments where reactions can occur efficiently. Similarly, in gas separation, removing one component from a gas mixture, you want large pores for rapid flow and small pores for selective separation based on molecular size. The large pores in the aerogel structure allow gas to move through the material quickly, while the micropores in the MOF can selectively allow small molecules to pass while blocking larger ones, or can preferentially adsorb certain molecules while allowing others to pass through. MOF aerogels represent a sophisticated approach to materials design, where you're engineering structure at multiple length scales simultaneously. The atomic scale of the MOF framework, the nanoscale of the aerogel network, and potentially the microscale or even macroscale of the final component shape. Each level of structure contributes something to the overall properties, and the combination can be more powerful than any single structural element alone. Another major category of aerogels comes from biology. Biopolymer aerogels can be biodegradable. These aerogels are made from natural polymers like cellulose, chitosan, alginate, or proteins. Cellulose, the main structural component of plants, can be processed into an aerogel that retains many of cellulose's desirable properties: mechanical strength, chemical stability, low cost, while gaining the aerogel's characteristic lightness and porosity. The biodegradability of these materials is significant. Traditional aerogels, particularly silica and many carbon aerogels, persist in the environment indefinitely. This isn't necessarily a problem for most applications, but in situations where you want a temporary material, perhaps packaging that degrades after use, or agricultural applications where you want the material to break down naturally. Biodegradable aerogels offer an advantage. They can perform their function during their useful life and then decompose naturally afterward, returning to the environment without leaving persistent synthetic materials behind. Cellulose aerogels, for instance, can serve as packaging material, providing excellent cushioning and thermal insulation during shipping, then being composted or naturally degrading after disposal. They can be used in biomedical applications like wound dressings, where the aerogel structure holds medication or promotes tissue regeneration, then gradually breaks down as the wound heals, eliminating the need for removal. The material has done its job and then simply disappears. Beyond biodegradability, polymer aerogels are tougher and more flexible than silica aerogels. Remember how we discussed silica aerogel being brittle under impact? Polymer aerogels address this limitation. The polymer chains that make up these aerogels can stretch and flex in ways that rigid silica networks cannot. When you apply force to a polymer aerogel, the polymer chains can orient themselves, distribute the stress, and deform without immediately fracturing. This improved toughness makes polymer aerogels more practical for applications where handling damage is a concern. You can bend them without cracking. You can compress them repeatedly without failure. Some polymer aerogels can be rolled up, folded, or otherwise manipulated in ways that would destroy silica aerogels. For applications like clothing insulation, where the material must withstand the bending and movement of fabric, or in packaging that gets handled roughly during shipping, this mechanical robustness is crucial. One persistent challenge with many aerogels, particularly silica, is their interaction with water. Unmodified silica aerogels are hydrophilic. They attract water. In humid environments, water molecules can adsorb onto the aerogel's surface, filling the pores and degrading the thermal insulation properties. In extreme cases, absorbed water can cause the structure to collapse. This moisture sensitivity limits where and how silica aerogels can be used. But hydrophobic aerogels resist moisture damage. Through chemical treatment, often attaching organic groups to the aerogel surface, the material's interaction with water can be reversed. Instead of attracting water, the modified surface repels it. Water droplets beat up on the surface rather than penetrating into the pores. The aerogel maintains its insulating properties even in humid conditions. It can even be immersed in water and then removed, shaking off the water and remaining dry internally. This hydrophobic modification has been crucial in enabling aerogels' use in real-world applications where moisture is present. Aerogel insulation in buildings, aerogel in outdoor clothing, aerogel in industrial applications. Most of these use hydrophobic aerogels to ensure reliable performance regardless of weather or environmental conditions. The modification typically adds minimal weight and preserves the aerogel's other desirable properties while making it far more robust in practical use. As we survey this variety of aerogel types, silica, carbon, graphene, metal oxides, MOFs, biopolymers, hydrophobic formulations, a fundamental principle becomes clear. Chemistry and structure together determine aerogel properties. You cannot understand an aerogel by knowing only its chemical composition. Two silica aerogels with different pore structures will behave differently. Nor can you understand it by knowing only its structure. A silica aerogel and a carbon aerogel with identical structures will have vastly different properties because silica and carbon are fundamentally different materials. The power of aerogels lies in this dual control. Through chemistry, you choose the basic material properties: electrical conductivity or insulation, chemical reactivity or inertness, mechanical strength or flexibility, thermal stability, optical properties, and countless other characteristics. Through structure, pore size, strut thickness, density, connectivity, hierarchical organization, you determine how these chemical properties manifest at the macroscopic scale, and you add properties that emerge from the structure itself, like exceptional thermal insulation or enormous surface area. This dual control makes aerogels incredibly versatile. Need electrical conductivity? Choose carbon. Need ultra-high temperature stability? Choose alumina or zirconia. Need biodegradability? Choose cellulose or another biopolymer. Need molecular scale separation? Incorporate MOFs. And in each case, the aerogel structure amplifies the chosen material's utility by maximizing surface area, minimizing weight, and creating pathways for transport of heat, electricity, or chemical species. The field of aerogel research continues to expand as scientists explore new material combinations and structures. There are metallic aerogels made from gold, silver, or other metals. Lightweight, conductive, and often catalytically active. There are composite aerogels that combine multiple materials in a single structure, perhaps carbon nanotubes embedded in silica, or MOF particles distributed through a polymer network, creating hybrid properties that neither material could achieve alone. Each new formulation represents an exploration of what's possible when you combine specific chemistry with aerogel structure. Some of these new materials will find applications and become commercial products. Others will remain research curiosities, interesting demonstrations of possibilities, but lacking a compelling application that justifies their cost and complexity. But each one adds to our understanding of how matter can be organized, how properties emerge from structure, and what becomes possible when we learn to build materials from the nanoscale up. As you consider the diversity of aerogels, from transparent silica to black carbon, from rigid ceramics to flexible polymers, from simple structures to hierarchical MOF hybrids, you're seeing the fruits of nearly a century of research building on Kistler's original insight. The fundamental idea of creating low-density, high-porosity solids through careful drying of gels has proven to be extraordinarily fruitful, applicable to an ever-growing range of materials and applications. In our next segment, we'll explore some of the most fascinating applications of aerogels, from capturing particles in space to insulating homes, from water purification to advanced electronics. But for now, rest with the understanding that aerogel is not a single material, but a broad category, a structural approach that can be applied to many different chemistries. The frozen smoke that captivated early observers was just the beginning. Now we have conductive aerogels, photocatalytic aerogels, biodegradable aerogels, aerogels that generate sound from light, and countless others. And in each case, we're seeing the same principle at work. Organize matter at the nanoscale into a specific structure, and properties emerge that the dense material alone could never achieve. We've explored how aerogel interacts with heat, with mechanical forces, with its own structure. But materials exist in a world filled with other forms of energy and information. Sound waves propagating through air, electromagnetic radiation spanning the spectrum from radio waves to light, vibrations and oscillations at countless frequencies. Aerogel's interaction with these phenomena reveals yet another dimension of its remarkable versatility, and demonstrates how its unique structure allows it to affect waves and radiation in ways that challenge our conventional understanding of how materials behave. Aerogels can absorb sound at specific resonant frequencies. Sound is a pressure wave traveling through a medium, compressions and rarefactions propagating through air or other materials. When sound encounters a surface, some reflects back, some is absorbed and converted to heat, and some may transmit through. Materials that absorb sound effectively are valuable for noise control, acoustic treatment of rooms, and vibration damping. Aerogel's interaction with sound is complex and fascinating. The nanoscale pores that make aerogel such an effective thermal insulator also affect how sound behaves in the material. When sound waves enter an aerogel, they cause the air in the pores to oscillate. This oscillation involves friction, air molecules rubbing against the pore walls, and this friction converts sound energy into heat, absorbing the sound. But the absorption isn't uniform across all frequencies. Different aerogel structures absorb different frequencies more effectively, based on the relationship between the sound's wavelength, the pore sizes, and the overall structure. At certain resonant frequencies, where the wavelength and structure align favorably, the aerogel can absorb sound particularly well. This frequency-dependent behavior means that aerogels can be designed to target specific noise frequencies, perhaps the low rumble of machinery, or the mid-range frequencies of human speech, or the high-pitched whine of electronic equipment. The form factor of the aerogel also matters significantly. Monolithic aerogels block sound better than granular fillings. A monolithic aerogel is a single, continuous piece. Imagine a tile or panel of aerogel. Granular aerogel consists of many small particles or beads of aerogel, perhaps packed into a cavity or mixed with other materials. While both forms have the aerogel's characteristic structure, the monolithic form provides better acoustic performance. This happens because sound waves encountering a monolithic aerogel must interact with the entire continuous structure. The wave enters the material and must navigate through the nanoscale pore network, experiencing friction and absorption throughout its path. But with granular aerogel, there are gaps between particles where sound can propagate more easily through air, reducing the total interaction with the absorbing structure. The discontinuous nature of granular packing creates pathways of less resistance that sound can exploit. Despite this, even relatively thin layers of aerogel can have substantial acoustic effects. Thin aerogel layers can increase sound transmission loss by over 10 decibels. Sound transmission loss measures how much sound is blocked when trying to pass through a barrier. Every increase of 10 decibels represents sound intensity being reduced to 1/10 of its original value. It's a logarithmic scale. So a 10 decibel improvement means that only about 1/10 as much sound energy passes through a dramatic reduction. Achieving this level of sound blocking with a thin, lightweight layer is remarkable. Traditional sound barriers often rely on mass, thick, heavy materials like concrete or multiple layers of drywall. The more massive the barrier, the more it resists being moved by sound waves, and thus the more sound it blocks. But aerogel achieves substantial sound blocking through a different mechanism, using structure rather than mass. A thin aerogel panel might weigh a fraction of what a comparable sound-blocking wall would weigh, yet provide significant acoustic insulation. This has practical implications for situations where weight matters. In vehicles, cars, aircraft, trains, reducing weight improves fuel efficiency and performance, but sound insulation is still necessary for passenger comfort. Thin, light aerogel acoustic barriers could provide noise reduction without the weight penalty of traditional materials. In buildings, lightweight acoustic panels could be easier to install and could allow for sound control without the structural requirements of heavy barriers. The acoustic properties of aerogels become even more interesting when we consider their potential as metamaterials. Aerogels can function as acoustic metamaterials. Metamaterials are engineered materials with properties not found in nature, achieved through structure rather than composition. Acoustic metamaterials can exhibit unusual behaviors like negative refraction of sound, creating acoustic cloaks that redirect sound around objects, or creating frequency band gaps where certain frequencies simply cannot propagate through the material. Aerogels, with their nanoscale structure that can be engineered and their ability to be formed into complex geometries, are natural candidates for acoustic metamaterial applications. By designing the aerogel structure, perhaps creating periodic patterns in density or pore size, or incorporating resonant elements at specific scales, researchers can create materials that manipulate sound in unprecedented ways. These might be used to create ultra-quiet environments, to focus or redirect sound for communication or sensing applications, or to protect sensitive equipment from acoustic vibrations. But sound waves aren't the only form of energy aerogels can interact with. Some aerogels absorb electromagnetic radiation. Electromagnetic radiation spans an enormous range, from radio waves meters long to gamma rays smaller than atoms, with visible light somewhere in the middle. Different materials interact with different parts of this spectrum in different ways, absorbing some frequencies while transmitting or reflecting others. The ability to control electromagnetic radiation is crucial for many technologies. We want materials that absorb radar to make stealth aircraft. We want materials that block harmful ultraviolet light while passing visible light for windows and sunglasses. We want materials that shield sensitive electronics from electromagnetic interference, stray radio waves, and electromagnetic fields that can disrupt circuits. Aerogels, particularly certain formulations, can serve these purposes. Carbon and metal oxide aerogels enable EMI shielding. EMI stands for electromagnetic interference, unwanted electromagnetic radiation that can cause electronic devices to malfunction. This interference might come from nearby electronic equipment, from power lines, from radio transmitters, or from countless other sources. Shielding against EMI typically requires conductive materials that can absorb or reflect the electromagnetic waves before they reach sensitive components. Carbon aerogels, being electrically conductive, can serve this purpose. When electromagnetic waves encounter the conductive carbon network, they induce currents in the material. These currents dissipate the wave's energy as heat, absorbing the radiation. The porous structure of the aerogel means that electromagnetic waves must interact with a large amount of surface area as they try to penetrate the material, enhancing the shielding effect. Metal oxide aerogels, depending on their specific composition and structure, can similarly interact with electromagnetic radiation through various mechanisms: absorption, scattering, or reflection. The advantage of using aerogels for EMI shielding is once again their lightness. Traditional shielding often uses metal sheets or foils, copper, aluminum, or specialized alloys. These are heavy and can be difficult to integrate into lightweight devices. An aerogel that provides comparable shielding while weighing a fraction as much would be valuable for portable electronics, aerospace applications, or anywhere that weight is a concern. Some formulations achieve truly impressive shielding performance. Cellulose, silver nanowire aerogels block nearly all 8 to 12 GHz radiation. This frequency range falls in the microwave region of the spectrum, overlapping with certain radar bands, satellite communication frequencies, and some wireless networking standards. Nearly complete blocking, perhaps 99% or more of the radiation absorbed or reflected, makes these aerogels extremely effective shields in this frequency range. These hybrid aerogels combine cellulose, providing the aerogel structure and biodegradability, with silver nanowires, providing electrical conductivity and strong interaction with electromagnetic radiation. The result is a material that's lightweight, potentially biodegradable, and exceptionally effective at blocking specific frequencies. Such materials might protect sensitive electronics in satellites from space-based radiation, shield wireless devices from interference, or create secure communication environments by preventing signal leakage. Yet another remarkable aspect of aerogel's interaction with radiation involves the distinction between different parts of the electromagnetic spectrum. Aerogels can be optically transparent, yet thermally opaque. This statement might seem contradictory at first. How can something be both transparent and opaque? The answer lies in recognizing that transparent and opaque depend on what frequencies we're discussing. Visible light, the narrow band of electromagnetic radiation our eyes can detect, spans wavelengths from about 400 to 700 nanometers. Thermal radiation, the infrared light that carries heat, extends from about 700 nanometers to perhaps 100,000 nanometers or more, with most thermal radiation at room temperature falling in the range of a few thousand to tens of thousands of nanometers. Some aerogels, particularly silica aerogels, transmit visible light quite well. They're transparent or translucent. You can see through them, though perhaps with some haziness or that characteristic blue tint. But these same aerogels strongly scatter or absorb infrared radiation. The infrared light cannot pass through as easily as visible light can. The aerogel is thermally opaque, blocking heat radiation even as it passes visible light. This decoupling of optical and thermal properties is unusual and valuable. Transparent aerogel windows trap heat while passing visible light. This is ideal for energy-efficient glazing. You want windows to let in daylight. Natural illumination reduces the need for artificial lighting. But you don't want windows to lose heat in winter or admit excessive heat in summer. Traditional windows struggle with this trade-off. Glass is transparent to both visible and infrared light, so a simple glass window lets heat pass readily. You can add coatings to reflect infrared, but these often reduce visible light transmission as well. Aerogel offers a better solution. A window incorporating aerogel can be highly transparent to visible light, letting in plenty of daylight, while being an excellent thermal insulator. The aerogel blocks heat loss through conduction, as we've discussed extensively, but it also blocks radiative heat transfer by being opaque to infrared. On a cold winter day, heat from inside the building cannot easily radiate through an aerogel window to the cold exterior. On a hot summer day, infrared radiation from the sun is partially blocked while visible light still enters. Buildings with aerogel windows can maintain comfortable interior temperatures with less heating or cooling, reducing energy consumption. The windows can be thinner than traditional insulated windows, which typically use multiple glass panes with air gaps, while providing equal or better thermal performance. And because aerogel is so light, these windows don't require heavy frames or supports despite their insulating capacity. This ability to selectively interact with different parts of the electromagnetic spectrum, passing visible light while blocking infrared, or passing certain radio frequencies while blocking others, exemplifies a broader principle. Aerogels decouple properties that are usually linked in materials. In most materials, certain properties tend to go together. Dense materials are usually strong and heavy. Materials transparent to light usually transmit heat as well. Materials that conduct electricity usually conduct heat. Materials that are rigid are usually brittle. But aerogel breaks these correlations. It can be strong yet light, providing load-bearing capacity with minimal weight. It can be transparent yet insulating, passing light while blocking heat. It can have high electrical conductivity, yet low thermal conductivity. Carbon aerogels conduct electricity well, but are still good thermal insulators because there's so little solid material for heat to conduct through. It can be rigid in compression, yet elastic under deformation, supporting loads without collapsing, but recovering shape after compression. This decoupling happens because aerogel's properties emerge from structure as much as from composition. In conventional materials, properties are largely determined by chemistry, what atoms or molecules make up the material. The same atoms arranged differently might give different properties, but there are limits. You can't make silica simultaneously strong and lightweight just by changing its chemistry. Dense silica will always be heavy relative to its volume. But with aerogels, you're engineering structure at the nanoscale. You're choosing how much solid material exists per unit volume, how it's arranged, how pore sizes are distributed. This structural control gives you access to combinations of properties that don't exist in dense materials. You can have something with silica's chemical inertness and thermal stability, but with density approaching that of air. You can have something with carbon's electrical conductivity, but with foam-like mechanical properties. You can have something with metal oxide's catalytic activity, but with the surface area of an entire basketball court in a single gram. This freedom to independently tune different properties makes aerogels extraordinarily versatile as engineering materials. When designing a component or system, engineers traditionally face trade-offs. Want better insulation? You'll have to accept more weight or thickness. Want better sound absorption? You'll need to add mass. Want to shield against electromagnetic interference? That'll add weight and might block light. Aerogels don't eliminate all trade-offs. They're still relatively expensive, still require careful handling in some cases, but they eliminate or greatly reduce many of the traditional trade-offs between properties. Consider a spacecraft. Every kilogram launched to orbit costs thousands of dollars in fuel and launch infrastructure. But spacecraft need thermal insulation for temperature extremes, need shielding from radiation, need acoustic dampening from launch vibrations, need structures that are stiff yet light. Aerogels address multiple needs simultaneously: thermal insulation with minimal weight, acoustic dampening without bulk, radiation shielding without heavy metals, structural elements that are rigid yet ultralight. A single material solving multiple problems, or at least reducing their severity, has enormous value in such demanding applications. Or consider buildings. Windows should let in light, but not heat loss. Walls should provide sound insulation, but not excessive thickness that reduces usable space. Insulation should resist fire, but not be toxic when burning. Aerogels can address these diverse requirements. Transparent aerogel windows, thin aerogel acoustic panels, fire-resistant ceramic aerogels. Each application takes advantage of aerogel's ability to combine properties that traditional materials struggle to achieve simultaneously. As we reflect on aerogel's interactions with sound, with electromagnetic radiation, with light and heat and structure, we're seeing different facets of the same fundamental principle. Engineer structure at the nanoscale, and you gain control over how materials interact with the world around them. The frozen smoke that captivated early observers turns out to interact with the world in ways as unusual as its appearance. Absorbing sound without mass, blocking heat while passing light, shielding against radiation while remaining lightweight, achieving through emptiness what dense materials achieve through substance. In our next segment, we'll explore more applications of aerogel, from environmental remediation to advanced electronics, and consider what the future might hold for this remarkable class of materials. But for now, rest with the understanding that aerogel is not just light, not just insulating, not just structurally interesting. It's a material that interacts with energy and waves in sophisticated ways, that decouples properties we usually think of as inseparable, that opens possibilities in engineering and design that simply don't exist with conventional materials. This is aerogel as wave manipulator, as radiation shield, as transparent insulator. A material whose structure at scales we cannot see determines how it interacts with phenomena at scales we can directly experience. Throughout our exploration of aerogel, we've focused primarily on its physical properties: how it insulates, how it bears loads, how it interacts with waves and radiation. But materials don't exist in isolation. They interact with the world around them, with the environment, with living systems, with the challenges we face as a society. And it's in these interactions, chemical, biological, environmental, that aerogel reveals yet another dimension of its versatility, moving from the realm of pure physics into applications that touch ecology, medicine, and everyday life. Aerogels can selectively absorb pollutants like heavy metals. Adsorption, where molecules or ions from a liquid or gas adhere to a solid surface, is one of the fundamental processes by which we can remove contaminants from water or air. The effectiveness of adsorption depends critically on surface area. The more surface area available, the more sites where contaminant molecules can attach, and thus the more efficiently the material can clean the contaminated medium. Here, aerogel's extraordinary surface area becomes a powerful tool. Remember that a single gram of aerogel can have the surface area of a basketball court, hundreds or even over 1,000 square meters. This vast internal landscape provides countless sites where pollutant molecules can be captured. When water containing heavy metals, lead, mercury, cadmium, chromium, flows through or contacts aerogel, these metal ions can attach to the aerogel surface, particularly if the surface has been chemically modified to attract these specific contaminants. The selectivity is important. Environmental cleanup often faces the challenge of removing specific harmful substances while leaving harmless ones behind. You want to remove lead from drinking water, but you don't want to remove calcium or other minerals that belong there. By tailoring the aerogel surface chemistry, perhaps adding functional groups that specifically bind to heavy metal ions, researchers can create materials that preferentially capture the pollutants you want to remove while ignoring the substances you want to keep. The process might work like this. Water contaminated with heavy metals is passed through a column packed with specially treated aerogel. As the water flows through the aerogel's porous structure, It makes intimate contact with that enormous internal surface area. Heavy metal ions collide with sites on the surface that have chemical groups specifically designed to grab them. Perhaps sulfur-containing groups that strongly bind to mercury, or carboxyl groups that capture lead. The ions stick to these sites, and the water that emerges from the other side of the column is substantially cleaner. Eventually, the aerogel's binding sites become saturated, but in some cases, the captured metals can be removed and the aerogel regenerated for further use. This application addresses a critical global challenge. Heavy metal contamination affects water supplies around the world, from industrial pollution to mining operations to aging infrastructure. Traditional water treatment can remove some of these contaminants, but often requires large facilities with substantial energy and chemical inputs. Aerogel-based systems could potentially offer more compact, more efficient alternatives, particularly for point-of-use applications or for treating specific contaminated streams. But water purification encompasses more than just heavy metals. Oil-absorbing aerogels enable lightweight environmental cleanup. Oil spills, whether massive disasters like tanker accidents or smaller incidents from industry or transportation, create environmental catastrophes, coating water surfaces, harming wildlife, and damaging ecosystems. Cleaning up oil spills has traditionally involved techniques like skimming oil off the water surface, using dispersants to break up the oil, or employing absorbent materials like polypropylene pads that soak up the oil. Aerogels, particularly hydrophobic aerogels made from carbon, cellulose, or other materials, can absorb oil while repelling water. The hydrophobic surface chemistry means water cannot penetrate the aerogel's pores, but oil, which is also hydrophobic, can. When you place such an aerogel in water with floating oil, the aerogel selectively absorbs the oil, drawing it into its vast internal pore structure. Because the aerogel is so light and porous, it can absorb enormous amounts of oil relative to its own weight, sometimes hundreds of times its mass in oil. The lightweight nature of these aerogels is crucial for practical deployment. Traditional absorbent materials, while effective, become heavy when saturated with oil, making them difficult to collect and transport. But even when fully loaded with absorbed oil, aerogel-based absorbents remain relatively light and easy to handle. They can be scattered across an oil spill, allowed to absorb oil, and then collected, perhaps with nets or mechanical collectors, for disposal or oil recovery. In some cases, the absorbed oil can even be squeezed out of the aerogel, allowing the material to be reused and the oil potentially recovered. This application exemplifies aerogel's potential for environmental benefit. The same structure that makes aerogel an exceptional thermal insulator, vast porosity, enormous surface area, low density, also makes it an effective tool for environmental cleanup. The structure captures and holds contaminants, while the lightness makes the material practical to deploy and recover. An emerging environmental challenge that aerogels are beginning to address involves an even smaller threat. Silk-based aerogels can remove microplastics with very high efficiency. Microplastics, tiny fragments of plastic, typically defined as smaller than 5 millimeters, have become ubiquitous environmental contaminants. They come from the breakdown of larger plastic items, from synthetic clothing fibers released during washing, from microbads in cosmetics, from tire wear, from countless sources. These particles persist in the environment, accumulate in water and soil, and have been found everywhere from ocean depths to Arctic ice to human bloodstreams. Removing microplastics from water is challenging because they're so small and because they're chemically similar to many materials we don't want to remove. But silk-based aerogels, made from the protein fibrin extracted from silk, have shown remarkable effectiveness at capturing these particles. The aerogel's porous structure creates a labyrinth that microplastic particles must navigate. As they flow through with water, many particles collide with the aerogel struts and adhere through physical trapping or weak chemical interactions. The silk protein surface chemistry can also be tuned to enhance attraction to plastic particles. Studies have shown removal efficiencies exceeding 95% in some cases, meaning that when contaminated water passes through Silica Aerogel, more than 95% of the microplastics are captured. And because silk is a natural biopolymer, these aerogels are biodegradable, addressing one environmental problem without creating another. After use, the microplastic-laden aerogel could potentially be incinerated for energy recovery or broken down through biological processes, rather than persisting as another form of waste. While environmental applications of aerogel are compelling, perhaps even more striking is aerogel's growing role in medicine and biology. The same structural features that make aerogels useful for environmental cleanup — high porosity, large surface area, lightweight nature — also make them valuable for interacting with living systems. Biopolymer aerogels can mimic extracellular tissue matrices. In our bodies, cells don't exist in isolation. They're embedded in extracellular matrix, a complex scaffold of proteins and polysaccharides that provides structural support, guides cell behavior, and facilitates communication between cells. When growing cells in the laboratory for research or medical applications, or when developing tissue engineering scaffolds that might eventually be implanted in patients, recreating this natural environment is crucial. Aerogels made from natural biopolymers like collagen, chitosan, alginate, or cellulose can provide scaffolds that cells recognize as similar to their natural environment. The porous structure of the aerogel mimics the porous nature of natural tissue, creating a three-dimensional environment rather than the flat surface of a traditional cell culture dish. Their pores support cell adhesion and nutrient diffusion. Cells can attach to the aerogel struts, spreading across the internal surfaces, much as they would attach to extracellular matrix in living tissue. The interconnected pores allow nutrients from the surrounding medium to diffuse throughout the structure, reaching cells in the interior, while waste products can diffuse out. This three-dimensional environment is more representative of how cells actually exist in the body. Cells grown on flat surfaces behave differently than cells in three-dimensional tissues. Their shape changes, their gene expression patterns change, their responses to drugs or other treatments change. By providing a three-dimensional scaffold, aerogels allow researchers to study cells in more realistic conditions, potentially leading to better understanding of disease and more accurate drug testing. For tissue engineering, growing replacement tissues or organs, aerogels offer a biodegradable scaffold that can guide tissue formation and then gradually disappear as the body's own extracellular matrix replaces it. Imagine an aerogel scaffold seeded with a patient's own cells, perhaps skin cells for treating burns or cartilage cells for repairing joints. The aerogel provides temporary structure, allowing the cells to organize and multiply, forming connections and depositing their own matrix. Over time, as the tissue matures, the aerogel scaffold breaks down and is absorbed or expelled, leaving behind living tissue that integrates with the patient's body. Aerogels also offer sophisticated control over drug delivery. In medicine, it's often not enough to simply administer a drug. The timing, location, and rate of drug release can be crucial for effectiveness and safety. Drug release rates can be controlled by pore size and connectivity. When a drug is loaded into an aerogel, perhaps by soaking the aerogel in a drug solution and then drying it, or by incorporating the drug during aerogel formation, the drug molecules are distributed throughout the porous structure. As the aerogel is exposed to body fluids, the drug gradually diffuses out. The rate of this release depends on how easy it is for drug molecules to travel through the aerogel's pore network. Small, well-connected pores might release drugs slowly, as molecules must navigate a tortuous path with many small passages. Larger, more open pores might release drug more rapidly. By engineering the aerogel structure, researchers can design release profiles, perhaps a quick initial burst followed by sustained slow release, or a steady constant release over days or weeks, or a delayed release that only begins after a certain time. This controlled release has numerous medical applications. For wound healing, You might want an initial burst of antibiotic to prevent infection, followed by sustained release of growth factors to promote healing. For cancer treatment, you might want localized, sustained release of chemotherapy drugs directly to the tumor site, rather than systemic administration that affects the entire body. For chronic conditions, you might want steady release of medication over extended periods, reducing the need for frequent doses. Cellulose aerogels enable advanced wound healing systems. Wounds require a careful balance of conditions for optimal healing. They need moisture but not excessive wetness. They need oxygen exchange. They need protection from infection. They often benefit from medication delivery. Traditional wound dressings like gauze provide some of these features, but not all. Advanced wound dressings try to create an ideal healing environment, and cellulose aerogels are increasingly used in these applications. A cellulose aerogel wound dressing might be loaded with antibiotics to prevent infection, with anti-inflammatory drugs to reduce swelling and pain, perhaps with growth factors or other biologics to accelerate healing. The aerogel's porous structure allows it to absorb wound exudate, the fluid that seeps from wounds, preventing accumulation that could slow healing or promote infection. At the same time, the pores allow oxygen to reach the wound, supporting the metabolic needs of healing tissue. The aerogel conforms to the wound shape, maintaining contact even with irregular surfaces. And as healing progresses, the cellulose aerogel can biodegrade, potentially eliminating the need for dressing changes that might disrupt newly formed tissue. Some advanced formulations even respond to wound conditions. Aerogels that change color in response to infection, releasing extra antimicrobial medication when bacterial activity is detected. Aerogels that adjust their moisture retention based on wound wetness, absorbing more when the wound is too wet or releasing moisture when it's too dry. These smart, wound dressings leverage aerogel structure to create responsive systems that actively participate in the healing process rather than just passively covering the wound. But aerogel's interaction with biology isn't limited to medical applications. Aerogels are used in cosmetics as ultralight anti-shine agents. This might seem trivial compared to water purification or tissue engineering, but it demonstrates how aerogel's properties can be valuable even in everyday consumer products. Skin naturally produces oils, and in some people or situations, this can create unwanted shine, particularly on the face. Traditional anti-shine cosmetics often use powder particles, silica, mica, talc, to absorb oil and scatter light, reducing shine. Aerogel particles, typically silica aerogel ground into a fine powder, perform this function exceptionally well. The aerogel's high porosity allows it to absorb many times its weight in skin oils, removing the shine-causing layer. The particles scatter light diffusely, creating a matte appearance. And because the particles are so light, remember, aerogel is mostly air. A small amount of aerogel powder can cover a large area without feeling heavy or noticeable on skin. The cosmetic feels light, almost imperceptible, while still providing the desired anti-shine effect. Moreover, they can increase SPF while remaining nearly imperceptible on skin. SPF, or sun protection factor, measures how well a product protects against ultraviolet radiation from the sun. Sunscreens typically contain UV-absorbing chemicals or UV-reflecting particles like zinc oxide or titanium dioxide. But these ingredients can make sunscreens feel heavy, look white or opaque on skin, or leave a noticeable residue. Aerogel particles can be incorporated into sunscreen formulations to scatter and reflect UV radiation, adding to the protective effect. Because the aerogel particles are so light, and because many aerogels are transparent or translucent to visible light, they can enhance sun protection without significantly affecting the sunscreen's appearance or feel. The result is a more protective product that doesn't sacrifice cosmetic elegance. It doesn't look heavy or white, doesn't feel greasy or thick, but still provides enhanced protection. These cosmetic applications might seem frivolous, but they actually highlight an important principle. High porosity allows aerogels to interact gently with biological systems. Biological tissues, skin, internal organs, living cells, are delicate. They're sensitive to mechanical stress, to chemical irritation, to anything foreign. Materials that interact with biology must be gentle, must not damage or excessively disturb the living systems they contact. Aerogel's high porosity and low density mean it's an inherently gentle material. When aerogel contacts skin, it doesn't press heavily or abrade. When cells grow on aerogel scaffolds, the structure yields slightly, accommodating the cells rather than constraining them rigidly. When aerogel absorbs wound exudate, it does so through capillary action in its pores rather than through compression or pressure. The material interacts through structure and surface chemistry rather than through mass or force. This gentleness is one reason why biopolymer aerogels work so well in medical applications. They provide structure and function without overwhelming the biological system. They're present, performing their role, delivering drugs, absorbing fluids, supporting cells, but they do so unobtrusively, allowing the biology to proceed with minimal interference. And when their job is done, many of these aerogels simply degrade and disappear, leaving no permanent trace. As we consider these applications, water purification, oil spill cleanup, microplastic removal, tissue engineering, drug delivery, wound healing, cosmetics, we're seeing aerogel as an interface material, something that mediates between different systems or between a system and its environment. The aerogel stands between contaminated and clean water, capturing pollutants. It stands between oil and water, selectively absorbing one while repelling the other. It stands between cells and culture medium, providing structure while allowing diffusion. It stands between wound and environment, protecting while healing proceeds. It stands between skin and sun, scattering UV while remaining nearly invisible. This role as an interface, as a mediator, emerges naturally from aerogel structure. The vast surface area means extensive contact with whatever the aerogel interfaces with. Lots of opportunity for interaction, for adsorption, for chemical reactions, for cell adhesion. The high porosity means fluids, nutrients, drugs, contaminants can move through the structure, allowing the aerogel to be an active participant in processes rather than just a passive barrier. The lightness means the aerogel can be present without dominating, can provide function without excessive burden. Looking at these diverse applications, from environmental cleanup to medicine to cosmetics, we see that aerogel's journey from laboratory curiosity to practical material continues to expand into new domains. Each application takes the same fundamental structure: nanoscale network, vast porosity, enormous surface area, minimal mass, and deploys it to solve a specific problem. The physics hasn't changed. The structure is still what it was. But by placing the structure in different contexts, by tuning the chemistry for different interactions, by engineering the details for different purposes, aerogel becomes useful in ways that would have seemed unimaginable to Samuel Kistler when he first removed liquid from a gel without collapse. In our next segment, we'll look toward the future, at emerging aerogel technologies, at challenges that remain, at what the next decades might hold for this remarkable class of materials. But for now, rest with this understanding. Aerogel doesn't just interact with physical forces like heat and sound and mechanical stress. It also interacts with chemistry, with contamination, with life itself. It can clean water and support cells, absorb oil and deliver drugs, protect wounds and enhance cosmetics. This is aerogel as functional interface, as active participant in chemical and biological processes, achieving through structure and surface what dense materials cannot achieve through composition alone. We've explored aerogel in laboratories, in medical applications, in environmental cleanup. But some of the most dramatic demonstrations of aerogel's capabilities occur in the most extreme environments humanity has created or encountered. The vacuum of space, the searing heat of atmospheric re-entry, the explosive violence of battery fires, the bitter cold of liquefied gases. In these demanding situations, where conventional materials struggle or fail entirely, aerogel often excels, proving that this gossamer substance is far tougher and more capable than its delicate appearance might suggest. NASA used aerogel to capture comet dust traveling at 6 kilometers per second. This statement encapsulates one of the most elegant scientific applications of aerogel ever conceived. In the late 1990s, NASA was planning the Stardust mission, a spacecraft that would fly close to a comet, collect samples of the dust and particles streaming from the comet's tail, and return these samples to Earth for analysis. The scientific value would be immense. Comets are pristine remnants from the formation of the solar system, and their composition could reveal details about the conditions that existed billions of years ago when planets were first forming. But there was a profound technical challenge. The spacecraft would encounter comet particles traveling at approximately 6 kilometers per second relative to the spacecraft, over 13,000 miles per hour. At these velocities, impacts generate enormous energy. If you tried to collect the particles by simply having them hit a solid surface, the impact would vaporize them. The kinetic energy of collision would convert to heat so rapidly and intensely that the particles would flash into gas, destroying the very samples you were trying to collect. You needed something that could stop the particles gently, despite their incredible speed. The Stardust mission avoided vaporizing particles on impact by using aerogel as the collection medium. The spacecraft carried panels of silica aerogel, tennis racket-sized frames filled with aerogel blocks. As the spacecraft flew through the comet's dust tail, particles traveling at 6 kilometers per second struck the aerogel and burrowed into it. The aerogel's structure provided gradual deceleration, instead of hitting a hard surface and stopping instantly, converting all kinetic energy to heat in a catastrophic instant. The particles plowed through the aerogel's nanoscale network, gradually slowing as they collided with strut after strut, creating carrot-shaped tracks through the material. Think of it like the difference between stopping a car by hitting a concrete wall versus driving into a huge snowbank. The wall stops you instantly, transferring all your kinetic energy in a violent jolt. The snowbank stops you gradually, allowing your kinetic energy to dissipate over distance and time. Aerogel, despite being a solid, behaves more like the snowbank. Its sparse structure yields, compresses, and breaks in front of the incoming particle, providing a gentler deceleration than a dense solid ever could. When Stardust returned to Earth in 2006, scientists carefully extracted the aerogel blocks and examined them. Throughout the material were thousands of tracks, each one created by a comet particle. At the end of many tracks, intact or partially intact particles remained, actual comet dust, preserved for analysis. The mission was a spectacular success, returning thousands of particles from both the comet and from interstellar space. Aerogel had performed a task that no other known material could accomplish, catching something traveling faster than a bullet while keeping it intact for study. This dramatic achievement in space science represents just one of many ways aerogel has proven valuable for space applications. The extreme environment of space, vacuum, radiation, temperature swings from hundreds of degrees above zero to hundreds below, demands materials with exceptional properties. Aerogel's reduce spacecraft thermal protection system weight by about 30%. This is an enormous advantage. In spaceflight, every kilogram of mass requires additional fuel to launch, and fuel has mass too, which requires more fuel to lift, creating a compounding problem. Reducing the weight of any spacecraft component creates cascading benefits throughout the entire mission design. Thermal protection systems shield spacecraft from extreme temperatures, particularly during atmospheric re-entry, when friction with air can heat surfaces to thousands of degrees. Traditional systems use thick layers of ablative materials or insulating tiles, both effective but heavy. Aerogel-based systems provide comparable protection with significantly less weight. That 30% weight reduction might translate to hundreds of kilograms saved on a large spacecraft, potentially allowing additional scientific instruments, more fuel for maneuvers, or simply making the mission possible with a smaller, cheaper launch vehicle. As space exploration advances, aerogel continues to play a role. Artemis missions incorporate aerogel insulation, The Artemis program aims to return humans to the Moon and establish a sustainable presence there, serving as a stepping stone toward eventual Mars missions. The spacecraft, habitats, and equipment for these missions face extreme thermal challenges. On the Moon's surface, temperatures swing from about 120 degrees Celsius in sunlight to negative 170 degrees Celsius in shadow. Equipment and habitats must maintain reasonable temperatures despite these extremes, and every kilogram matters for missions traveling beyond Earth orbit. Aerogel insulation helps manage these thermal challenges while minimizing weight. Habitat modules, spacesuits, scientific instruments, storage containers. Many components benefit from aerogel's exceptional insulation in a lightweight package. As missions extend farther and longer, eventually to Mars, where missions might last years and resupply is impossible, the efficiency advantages of aerogel become even more valuable. But aerogel's utility in extreme environments isn't limited to space. Back on Earth, another emerging technology presents thermal challenges that aerogel is helping to address. Aerogels help prevent thermal runaway in EV batteries. Electric vehicles rely on lithium-ion batteries for energy storage. These batteries pack enormous energy density into relatively small spaces, making electric vehicles practical. But this energy density comes with risk. If a battery cell is damaged, overcharged, or develops an internal short circuit, it can overheat. This heating can trigger a chain reaction called thermal runaway, where the heat causes chemical reactions that generate more heat, which accelerates the reactions further, leading to fire or explosion. In battery packs containing hundreds or thousands of cells, preventing thermal runaway from spreading is crucial. If one cell fails, you want to prevent it from heating its neighbors, which would trigger their failure, cascading through the entire pack. This requires thermal barriers between cells, materials that insulate well enough to slow heat transfer, giving safety systems time to respond, but that don't add excessive weight or bulk to the battery pack. Aerogel provides an ideal solution. Thin aerogel barriers between cells or groups of cells can provide substantial thermal resistance with minimal added weight and volume. If one cell enters thermal runaway, the aerogel slows the heat transfer to adjacent cells, potentially containing the failure to a single cell or small group, rather than allowing it to propagate through the entire battery. This safety enhancement is becoming increasingly important as battery packs grow larger and energy density increases. When thermal runaway does occur despite preventive measures, rapid response is critical. Aerogel-based blankets can extinguish EV battery fires in about 90 seconds. Battery fires are notoriously difficult to fight. The fire is fueled by chemical reactions within the battery itself, not just by combustion of surrounding materials. Pouring water on a battery fire can be ineffective or even dangerous. The fire can reignite hours after apparently being extinguished. Traditional firefighting methods often involve containing the fire and letting it burn itself out, which can take hours and result in total vehicle loss. Aerogel fire blankets work differently. These are large, flexible blankets with aerogel insulation that can be quickly draped over a burning electric vehicle. The aerogel's exceptional thermal insulation prevents heat from the fire from radiating outward while containing the fire's heat, accelerating the consumption of available fuel. The blanket limits oxygen access, suppressing combustion of external materials. Within approximately 90 seconds, the fire is typically extinguished or reduced to a point where conventional methods can finish the job. The rapid suppression prevents fire spread to nearby vehicles or structures and reduces toxic smoke exposure for firefighters and bystanders. This application demonstrates aerogel moving from aerospace and specialized industrial uses into everyday safety equipment. As electric vehicles become more common, fire departments worldwide are acquiring aerogel fire blankets as part of their standard emergency response equipment. What was once an exotic material used by NASA has become a practical tool for protecting public safety. Beyond vehicles and spacecraft, aerogel addresses thermal challenges in industrial infrastructure. Aerogels insulate LNG pipelines and cryogenic storage tanks. LNG, liquefied natural gas, exists at -160 degrees Celsius. At this temperature, natural gas becomes a liquid, reducing its volume by a factor of about 600 compared to gas at room temperature. This makes LNG practical to transport by ship or store in tanks, enabling natural gas to be moved from where it's produced to where it's needed, even across oceans. But maintaining this extreme cold requires exceptional insulation. Any heat leaking into the LNG causes some of it to boil off, both wasting valuable fuel and potentially creating pressure problems in storage tanks. Traditional cryogenic insulation often uses perlite, a lightweight volcanic glass, or foam materials. These work, but they're not as effective as aerogel. Heat loss reductions can reach about 85% compared to perlite. This is a dramatic improvement. An LNG storage tank insulated with aerogel instead of perlite loses only 15% as much heat, meaning far less LNG boils off, less product is wasted, and the refrigeration systems maintaining the cold temperature require less energy. For large facilities storing thousands or millions of gallons of LNG, these efficiency gains translate to substantial cost savings and environmental benefits through reduced energy consumption. The same principles apply to pipelines carrying cryogenic fluids. Aerogel pipe insulation maintains the fluid's temperature over long distances with minimal heat leak. This is particularly valuable for industrial processes that use liquid nitrogen, liquid oxygen, or other cryogenic fluids, where maintaining proper temperature throughout the distribution system is essential for process efficiency and safety. But aerogel's industrial applications aren't limited to extreme cold. Industrial steam systems save 15 to 20% energy using aerogel insulation. Many industrial facilities use steam for heating, for driving machinery, or for process needs. Steam is generated in boilers and distributed through pipes throughout the facility. Any heat lost from these pipes is wasted energy. You've paid to heat the water into steam, and if that heat escapes before the steam reaches where it's needed, you've wasted fuel. Traditional pipe insulation, fiberglass, mineral wool, calcium silicate, provides some protection, but aerogel performs better. The superior thermal resistance means less heat escapes, so more of the energy you paid for actually reaches where it's needed. A 15 to 20% energy savings across an entire industrial steam system can represent enormous cost reductions and environmental benefits. A large factory or processing plant might save hundreds of thousands of dollars annually in fuel costs, while reducing carbon emissions proportionally. The thin profile of aerogel insulation is an additional advantage in industrial settings. Because aerogel insulates so effectively per unit thickness, you can achieve excellent thermal performance with thinner insulation. This matters when insulating pipes in crowded areas where space is limited, or when retrofitting insulation onto existing systems where bulky insulation might not fit. An aerogel blanket just a centimeter or 2 thick might provide insulation equivalent to 5 or 10 centimeters of traditional material, making installation feasible in situations where conventional insulation would be impractical. These diverse applications, spacecraft thermal protection, particle capture in space, battery safety in electric vehicles, LNG infrastructure, industrial steam systems, share a common thread. They're all extreme environments where conventional materials struggle. Space presents vacuum, radiation, and temperature extremes. Battery fires create intense heat and toxic conditions. Cryogenic systems operate at temperatures that make most materials brittle and ineffective. Industrial steam systems subject insulation to high temperatures, mechanical vibration, and harsh conditions over years of continuous operation. Aerogels operate reliably in extreme engineering environments. This reliability stems from aerogel's fundamental nature. There's no single component that can fail catastrophically. Unlike a complex device with moving parts, aerogel is simply structure, a network of solid material and pores. It doesn't have mechanisms to jam, seals to leak, or electronic components to malfunction. As long as the basic structure remains intact, the aerogel continues performing its function. The temperature stability we discussed earlier means aerogel maintains its properties across enormous temperature ranges. The same aerogel formulation might insulate liquid nitrogen at -196 degrees Celsius and withstand furnace temperatures above 1000 degrees Celsius. This versatility reduces the need for different materials for different temperature regimes. One material can potentially handle the full range of temperatures encountered in complex systems. The chemical stability of many aerogels means they resist degradation from exposure to chemicals, moisture, or environmental conditions that would destroy other materials. Hydrophobic silica aerogels shed water, preventing moisture-related degradation. Carbon aerogels resist oxidation and chemical attack. Ceramic aerogels withstand corrosive environments. This durability means aerogel components can remain in service for years or decades with minimal maintenance, crucial for applications like industrial infrastructure or spacecraft where replacement is difficult or impossible. The mechanical properties, while sometimes a concern for handling during installation, actually serve aerogel well in its operating environment. The slight elasticity under compression means aerogel can accommodate thermal expansion and contraction, vibration, or settling without cracking as a rigid material might. The brittleness under sharp impact matters less once the aerogel is installed and protected from such impacts. In its actual use environment, between pipe and outer jacket, within a battery pack, on a spacecraft surface, the aerogel experiences the kinds of forces it handles well while being protected from the kinds it doesn't. As we consider aerogel in these extreme applications, flying through comet tails at 6 kilometers per second, protecting spacecraft during re-entry, containing battery fires, insulating cryogenic fluids, surviving years of industrial service, we're seeing the full realization of aerogel's potential. This material that looks so delicate, that seems like it might blow away in a breeze, performs reliably in conditions that would defeat many materials that appear far more robust. There's something profound in this contrast between appearance and capability. Aerogel teaches us that effectiveness doesn't require bulk, that strength doesn't require mass, that reliability doesn't require density. Through clever structure at the nanoscale, through engineering emptiness itself, aerogel achieves what dense, heavy materials struggle to accomplish. It captures particles moving faster than bullets without destroying them. It insulates spacecraft with a fraction of traditional system weight. It contains battery fires in seconds. It maintains cryogenic temperatures while losing minimal heat. It saves industrial facilities millions in energy costs. In our final segment, we'll look toward the future of aerogel, at emerging applications, at challenges yet to be solved, at what the coming decades might hold for this remarkable material. But for now, rest with the image of aerogel in action in the harshest environments humanity has encountered. In the vacuum of space, in the violence of battery fires, in the extreme cold of liquefied gases, in the demanding conditions of industrial systems. This is aerogel as reliable performer, as trusted component, as material that looks like frozen smoke, but functions like one of the most capable substances ever created. We've journeyed through aerogel's properties, its history, its structure at scales we cannot see, and its applications in environments from the human body to the depths of space. Now, as we approach the end of our exploration, we turn our attention to the present moment and to what lies ahead. Aerogel stands at a pivotal point in its evolution from scientific curiosity to indispensable industrial material, and the trajectory of its growth suggests we're witnessing the early stages of a transformation in how we build, insulate, protect, and engineer the technologies that shape our world. The global aerogel market reached about $1.27 billion in 2025. This figure represents more than just economic activity. It's a measure of aerogel's transition from niche specialty to mainstream engineering material. To put this in perspective, when Samuel Kistler first created aerogel in 1931, there was essentially no market at all. For decades, aerogel remained confined to laboratories and a handful of specialized applications. Even as recently as the early 2000s, the aerogel market was measured in tens of millions of dollars, serving primarily aerospace and a few industrial niches. The growth to over $1 billion in annual market value represents exponential expansion. This growth reflects multiple factors converging simultaneously. Manufacturing costs have decreased as production methods improved and economies of scale began to apply. New applications have emerged as engineers in various fields discovered how aerogel could solve problems that conventional materials couldn't address effectively. And perhaps most importantly, certain megatrends, electrification of transportation, focus on energy efficiency, space exploration initiatives, have created enormous demand for exactly the properties aerogel provides. Among these trends, one sector stands out for particularly rapid growth. EV-related aerogel applications are growing rapidly. Electric vehicles represent one of the most significant technological transitions of the 21st century. Governments worldwide are setting timelines for phasing out internal combustion engines. Consumers are increasingly choosing electric vehicles for their performance, efficiency, and environmental benefits. Automotive manufacturers are investing hundreds of billions of dollars in electrification. And every one of these electric vehicles needs thermal management solutions, insulation to maximize battery efficiency, barriers to prevent thermal runaway propagation, materials that provide safety without excessive weight. Aerogel addresses all of these needs simultaneously. A single aerogel component in a battery pack might provide thermal insulation to maintain optimal battery temperature, thermal barriers to prevent runaway propagation, and weight savings compared to conventional alternatives. As electric vehicle production scales from millions to tens of millions of vehicles annually, the demand for aerogel components grows proportionally. Industry analysts project that EV-related applications could become the largest single market segment for aerogel within the next decade, potentially exceeding all other applications combined. The industry has responded to this demand with substantial investment in production capacity. LG Chem opened the world's largest aerogel plant in 2025. LG Chem, a major Korean chemical company and battery manufacturer, recognized both the opportunity and the strategic importance of aerogel for electric vehicle applications. Their decision to build a dedicated aerogel production facility, and to make it the largest in the world, signals confidence that aerogel demand will continue growing substantially. This facility's annual production capacity reached about 200,000 square meters. To visualize this scale, imagine 200,000 square meters of aerogel blankets or panels. That's roughly equivalent to covering 30 football fields with aerogel material every year from this single facility. This represents a dramatic scaling up from the production levels of even a few years ago, when aerogel manufacturing was measured in thousands of square meters annually across all producers worldwide. The construction of such large-scale production infrastructure indicates that aerogel has moved beyond the phase where supply constraints and high costs limited adoption, entering a phase where economies of scale begin to drive costs down further, enabling even broader application. LG Chem isn't alone in expanding aerogel production. Aspen Aerogels captured a majority share of new EV thermal contracts. Aspen Aerogels, an American company that has focused on aerogel development and production for years, has positioned itself as a primary supplier to the automotive industry. Their success in securing contracts with major automakers reflects both the technical maturity of their products and the automotive industry's commitment to incorporating aerogel into vehicle designs. These contracts typically span multiple years and multiple vehicle models, providing Aspen and other aerogel manufacturers with predictable demand that justifies further investment in production capacity and research. The majority market share in new EV thermal contracts suggests that aerogel has moved from interesting alternative we're testing to preferred solution we're designing around in the automotive engineering community. Engineers are no longer asking, should we consider aerogel? But rather, how can we best incorporate aerogel into our design? Beyond transportation, aerogel continues expanding into the built environment. Aerogel integrated buildings have achieved LEED Platinum certification. LEED leadership in energy and environmental design is a widely recognized green building certification system. Platinum is the highest certification level, requiring exceptional performance in energy efficiency, sustainable materials, indoor environmental quality, and other factors. Achieving LEED Platinum is demanding, and every component of the building contributes to or detracts from this goal. Buildings incorporating aerogel insulation have demonstrated that this material can play a significant role in achieving top-tier sustainability performance. Aerogel's superior thermal insulation allows thinner walls that provide better energy efficiency than thick conventional walls, reducing heating and cooling energy consumption, often the largest component of a building's environmental footprint. The thin profile means more usable interior space for the same exterior footprint, improving space efficiency. In retrofit applications, aerogel can dramatically improve the performance of existing buildings without requiring major structural changes, enabling sustainability improvements to the existing building stock, not just new construction. The fact that multiple aerogel integrated buildings have now achieved LEED Platinum certification establishes a track record that makes aerogel more attractive to architects and developers. It's no longer an experimental material with uncertain performance, but a proven component of award-winning sustainable buildings. This recognition helps drive aerogel's adoption in the construction sector, which is enormous, orders of magnitude larger than aerospace or even automotive, and could represent aerogel's largest long-term growth opportunity. Manufacturing innovation continues to expand what's possible with aerogel. Large-scale 3D printed aerogels enable custom structural designs. We mentioned additive manufacturing earlier, but the ability to print aerogel structures at large scale represents a significant advancement. Instead of being limited to simple shapes, sheets, blocks, cylinders, engineers can now design aerogel components with complex internal geometries optimized for specific functions. Imagine an aerogel thermal barrier for a battery pack with varying thickness. Thicker where thermal resistance is most critical, thinner where space is limited. Or an aerogel acoustic panel with internal channels designed to target specific frequencies of sound. Or an aerogel structural component that's dense and strong in load-bearing regions, but light and porous elsewhere, optimizing the strength-to-weight ratio. 3D printing makes these designs practical, allowing performance optimization that wouldn't be possible with traditional manufacturing methods. As the technology matures and scales, we may see aerogel components that are designed and manufactured as integrated systems rather than as simple panels or blankets. An entire spacecraft thermal protection system, printed as a single piece with varying properties in different regions. A building's complete insulation system, with aerogel formulated and structured differently for walls, roofs, windows, and foundations, all optimized for their specific conditions. The combination of aerogel's versatile properties and additive manufacturing's design freedom creates possibilities that are only beginning to be explored. Looking at aerogel's current trajectory and emerging applications, certain themes become clear. Aerogels enable lighter, safer, and more efficient technologies. These three attributes, lightness, safety, efficiency, are increasingly valuable in a world facing challenges of energy consumption, resource constraints, and environmental impact. Lightness matters because transportation, whether of goods or people, requires energy proportional to weight. Every kilogram saved in a vehicle, aircraft, or spacecraft translates directly to energy savings over the vehicle's lifetime. Lightness also matters in structures, where lighter buildings require less robust foundations and structural support, reducing material use and construction cost. Safety matters because technologies are becoming more powerful and more complex, often containing substantial stored energy. in batteries, in pressurized systems, in high-temperature processes. Managing this energy safely, ensuring that failures don't cascade catastrophically, protecting people and property when things go wrong. These are fundamental engineering challenges where aerogel's thermal properties provide crucial capabilities. Efficiency matters because energy waste represents both economic cost and environmental impact. Every watt of heat lost through inadequate insulation must be replaced by burning fuel or consuming electricity. Every degree of temperature deviation from optimal in a battery or industrial process represents reduced efficiency and increased wear. Aerogel's exceptional insulating properties directly address these efficiency concerns, allowing systems to operate closer to their theoretical performance limits. As we reflect on aerogel's journey, a remarkable transformation becomes apparent. Once a laboratory novelty, aerogel is now industrially essential. There was a time, not so long ago, when aerogel was something you might see in a museum display or a science demonstration, a curiosity that prompted wonder and questions, but had little practical impact on daily life. That time has passed. Today, aerogel components are being installed in thousands of buildings, insulating homes and offices. They're being integrated into hundreds of thousands of electric vehicles, making these vehicles safer and more efficient. They're protecting industrial infrastructure, saving energy in factories and processing plants. They're enabling space missions, supporting scientific research, advancing technologies across dozens of industries. For many applications, aerogel isn't an interesting option. It's the preferred solution, sometimes the only practical solution. This transition from novelty to necessity took decades and required contributions from countless researchers, engineers, and entrepreneurs. It required solving manufacturing challenges, reducing costs, proving reliability, educating potential users, and building production infrastructure. But the transition is now largely complete. Aerogel has arrived as a mature, industrial-scale material. And yet, in another sense, we're still in the early stages of aerogel's story. The world's lightest solid is shaping the future of advanced engineering. The applications we see today, vehicles, buildings, industrial systems, represent aerogel addressing current needs. But materials often enable technologies we haven't yet imagined. The development of semiconductors enabled computers, but the scientists working on early semiconductors couldn't have predicted smartphones or artificial intelligence. The development of fiber optics enabled global communications, but early optical fiber researchers couldn't have envisioned the internet as we know it. What might aerogel enable that we haven't yet imagined? Perhaps ultralight structures for space habitats, making permanent human presence beyond Earth practical. Perhaps buildings so energy efficient that they require almost no heating or cooling, transforming architecture in extreme climates. Perhaps battery systems so safe and efficient that energy storage becomes trivial, enabling complete transition to renewable energy. Perhaps medical devices that interact with the body in entirely new ways, enabled by aerogel's biocompatibility and unique properties. Some of these possibilities will materialize. Others won't. But history suggests that versatile materials with unusual properties tend to find applications far beyond their original intended uses. Aerogel's combination of lightness, porosity, thermal properties, and structural versatility makes it exactly the kind of material that could enable breakthrough technologies in fields we haven't yet considered. As manufacturing continues to scale and costs continue to decline, aerogel will likely become ubiquitous in ways that are currently difficult to predict. Perhaps there will come a time when aerogel is as common and unremarkable as fiberglass insulation is today, present in every building, every vehicle, taken for granted rather than marveled at. That transition from remarkable to ordinary is, in its way, the ultimate success for a material. It means the material has become so useful, so reliable, so cost-effective that it's simply the obvious choice, the standard solution, the foundation on which other technologies are built. But even as aerogel becomes commonplace, its fundamental nature remains extraordinary. A solid made of almost nothing, structure without substance, emptiness organized into utility. The physics hasn't changed since Kistler's first synthesis in 1931. Thermal conductivity still depends on suppressing heat transfer through solid, gas, and convection. Mechanical properties still emerge from the bending of nanoscale struts. The surface area still scales with porosity. The beauty of aerogel lies in how these simple principles, carefully implemented at the nanoscale, create a material with properties unlike anything else. As we conclude our exploration of aerogel, we return to where we began, with wonder at a material that challenges our intuitions about what matter can be. Something lighter than air, yet solid. Something transparent, yet thermally opaque. Something fragile, yet capable of supporting thousands of times its own weight. Something that looks like frozen smoke, yet functions as one of humanity's most capable engineering materials. Aerogel reminds us that the material world still holds surprises, that there are still possibilities waiting to be discovered in how we organize atoms and molecules. It demonstrates that cleverness in design can achieve what brute force cannot, that structure can matter as much as composition, that emptiness can be as functional as substance. And it shows that the journey from scientific curiosity to practical necessity can take decades, requiring patience, persistence, and the contributions of many people pursuing a vision of what could be. The world's lightest solid, mostly air, barely there, yet remarkably present in its effects on the technologies shaping our future. From the comet dust captured in space to the batteries in electric vehicles, to the insulation in green buildings to applications not yet imagined, aerogel continues its improbable journey from laboratory bench to industrial necessity. And in that journey, we see reflected the broader story of materials science itself, the patient work of understanding how matter behaves, of learning to control structure at ever smaller scales, of translating that understanding into materials that expand what's possible. As you rest tonight, perhaps in a building insulated with aerogel, or having traveled in a vehicle protected by aerogel, or simply having encountered this remarkable material in ways you might not even recognize, you can rest knowing that the world of materials continues to evolve, that human ingenuity continues to find new ways to organize matter, and that sometimes the most extraordinary capabilities come from the most unlikely sources, from frozen smoke, from solid air, from the world's lightest solid, shaping the future one nanoscale strut at a time.